Hello, everybody. I'm Lorena Barba, and here is Tingyu Wang. He's one of the senior PhD students in my lab, and he and I wrote this material together, and we'll be presenting together. I'll start, and Tingyu will help a lot, hopefully. Juan over here has volunteered to be a helper and walk around and help you out if you have any issues, if you run into errors or something. Now, before we get started, I wanted to have an idea about you here in the room. So let me ask, how many here in the room have perhaps an engineering degree or a science degree and have a vague recollection of having taken a linear algebra class in undergraduate at some point? All right, I'm going to say that's almost everyone. Okay. Anyone here who has actually never taken a linear algebra class at all? It's okay, because I'm not going to assume much knowledge at all, but okay. Now, this was advertised as a beginner tutorial, and it is, in fact, the case that we are going to start from zero, depending on how time works out, from 0 to SVD is the plan. But, so if you have taken a class in linear algebra and maybe remember some of it, it could be that in the beginning it's a little bit slow. And just a disclaimer here that that's by design, that we want to bring everybody to a level of recollection and not assume anything. So we really start from zero, defining and trying to remember what a vector is, right? From total zero. Now, if you remember taking an undergraduate class in linear algebra, you may have experienced that class was proof-based. It is the case that in many science degrees and in many engineering degrees, linear algebra is offered in the designs of today's curriculum as the first proof-based course in mathematics, usually given by a mathematics professor doing a service class for engineering. It's usually a proof class. It's the first class where students are exposed to the methods of proving theorems often. And there is a lot of manipulations, there's a lot of solving things on a piece of paper. What we have wanted to do here, and inspired by several other sources as well, is to write a tutorial on linear algebra that avoids all of that. And instead of doing, going through any proof of a theorem, we explore things computationally, graphically, to bring out the ideas that we're trying to understand, to make them make sense to us, to the point that we feel that it's a proof. It is, in fact, a proof, but we are proving things in a non-formal way, using computation, using graphical representations of our ideas. So, as you may have heard in our ramblings before we started, I am not on the Slack channel. In fact, it wouldn't be very practical for me to try to follow the Slack channel while I'm presenting. So Juan, who is offered to be the helper, is monitoring the Slack channel and to see that if you have help, if you need help or you're posting a link or something, he can help out with that. Tingyu is also not on the Slack channel, I believe, so he cannot help you with that. We have one Slack master over here. Okay, and so my question to you is if you've all identified the location of this repository where we have all the materials. If anyone has not located this repository, then just raise your hand. Juan is going to run to you because he's a master in helping out people to get up and running. Anyone need help with locating this repository? Okay, Tingyu, we forgot to add the binder button. I just remembered. Could you do that while we? Yeah. Okay. If anybody wants to use binder, then we can just add it to the top of the README. Okay. If you've cloned this repository, and we're using really standard packages, so we hope that you don't need to really install anything outside of your normal Jupyter Python installation. We're using Python 3. And, but if you need to install it, then we do have a requirements .txt and environment YAML. If you need help with any setting up your environment and anything, I'm not going to spend time here doing it. We're going to rely on you raising your hand and Juan going around and helping you with that. But the way that we're going to do this is, even if you don't have a clone of these the materials in your laptop, you can follow along, because what we're going to do, each one of these lessons here has a link to the NBViewer rendered version of this lesson. So if you clicked on lesson 1, you can just pull it up as a web page, and it is there available for you to follow along. But what we're going to do is we're going to just start a new blank notebook. Oh, well, you do need to have a clone because you're going to need our helper functions. Okay, so take that back. This is my local version of the notebooks, the 4 lessons. And what we're going to do is open a brand new clean notebook and start essentially following along the steps of the lesson, so that you're typing those commands, paying attention and of what you're doing instead of just reading through. And also have the opportunity to experiment and change things around. And with that interaction, hopefully the ideas that we are discussing become more clear to you. Because we all know that a one-way presentation, the so-called lecture, gives you the impression of clarity and of understanding, but when you actually try to do stuff, you realize that it was an illusion, right? It was an illusion of the illusion of competence. That's normal. It happens to everyone. So the only way that we can improve on that is actively manipulating the concepts, and we take advantage of Python and Jupyter to do that, and it helps us out to have sort of a conversation. All right, so what we're going to do is open a brand new notebook. You can call it whatever you want. My lesson 1, all right, on linear algebra. You can leave some notes to self, perhaps. You want to do my lesson 1 on linear algebra. Just maybe you can leave here a link to the I'm going to close this. We already know that we are in the tutorial on linear algebra. We've introduced everybody. So, and I've somehow gotten rid of my GitHub page where the public version of the notebooks are, because I've pulled it up from here. So I'm just going to find it again, and maybe you can add a link to it or something like that. So this is how we're going to go around, going to go about the executing the lesson today. As always, we start with our favorite libraries of the Python world. So we're going to import NumPy, import matplotlib, and get ready for that. We do the complete import NumPy is our style. If you want to do import NumPy as, if you want to do the alias NP, that's up to you. But we like to be explicit in the beginner lessons. So matplotlib inline to get our nice figures, and from matplotlib import pyplot. So please do follow along so that you get this experience of changing things around as we do. Now, we have additionally a helper script to provide graphical output for us to help us with this tutorial. Now, I point out that one of the things that you can do is to have one window or one tab with this active notebook where you're playing with things, and then you can have another tab with the full written out lesson that actually has a narrative and explains things, and you can revisit this after today to read things that you might have, you spaced out for a bit. It's all written out in a fully narrated notebook. And we have all of the commands here also available. So sometimes we can cheat a little bit, and for example, I don't want to type all this, I'm going to just copy and paste from here. You could do that, or you could, I don't recommend that we copy and paste, okay? Let's not do copy and paste because then you don't really pay attention to what's happening. But I'm gonna cheat with this little bit here because, to save a bit of time, especially because when I'm speaking, I'm typing at the same time, I make mistakes. And so what we're doing here is appending the path to where we have the scripts. In the GitHub repository, you'll see that we've created a little structure here where we have some images that we're loading in the notebooks themselves, and we have some scripts on our CSS style right here. And so these scripts, we want to make sure that we can access. These are the plotting scripts that are going to help us create beautiful representations of the vectors and the transformations and everything. I also will use the rendered version of the notebook instead of a slide sometimes to show you the figures that we have here. All right, so let's start from absolute zero. What is a vector? Here we take inspiration from some nice videos that are available online, and we give you the link here so that you can follow them and watch them later because they're really recommended, highly recommended. And so we leave you these references for you to continue studying. And in this video, it's presented that the vector, depends on who you are, what a vector means to you. The typical representation of a vector that we see is the physicist's point of view in a mechanics class, where a vector is an arrow that has a direction and a length or magnitude. That's the physicist's point of view. From the mathematician's point of view, a vector is actually this very abstract object that behaves in a certain way when it's multiplied by a scalar, that behaves in a certain way when it's added together so that you can construct combinations of them. It's an abstract object. For the computer scientist, a vector is a list of numbers, an ordered list of numbers. So it depends on which point of view you are, how you view a vector. So here's a picture, the physicist vector and a computer scientist vector. But we start with the physicist approach, where we can draw things as arrow because that's intuitive. We move to higher dimensions. It gets harder to represent things as arrows, and then we eventually move to the idea of a vector as a list of numbers, and then we can generalize that to applications, many applications. So the idea of a vector depends on who you are. All right, so we have a nice facility here to plot vectors with the little helper function. So let's create a vector. We're going to create a vector, or rather we can create a list of vectors, but my list here that I'm going to call vectors, it really has only one vector in it. It's a list, and I'm just going to give the coordinates of a vector 2, 2. That defines a vector. I could add more vectors with a comma here, but I'm just going to do one here at the moment. We're going to, the helper function that we have allows us to provide vectors and the position of the tails, where we want those vectors to be plotted. So let's create a list with, well, we could do 2 or 3 tails. I have 4 here. Each one is going to be a set of coordinates. So let me do the ones that I have here, -3, -2. I'm going to add another one here, -3, 1. We're going to add another one here. It's the origin, 0, 0, the origin of a Cartesian coordinate system. And finally, maybe 1, -3. That is just a list. I have an extra parenthesis here. Keep an eye out for my typos, because obviously when you're speaking and typing at the same time, you make mistakes. And then we can call this function called plot vectors, vector without an S, plot vector, that's the name of our function, is our helper function. And we give it as argument the Python variable called vectors, where we have this list of vectors that is only just one element, and another list that is the list of tails. And we execute that, and out comes a little representation of Juan. I'm just wondering if you can make the font a little bigger. Of course. Thank you so much for saying that. And let me take advantage of all the space that I have. Is that good? Or is that still small? Let's do that. All right, so let me also get rid of the header and the toolbar to get a little more space. Okay? So this is what we've done here. We've created a list of vectors using the coordinate values and a list of tails, and plot under dash vector receives those two lists and provides a representation of these vectors. So as you can see, the vectors here, really, remember, only one vector. We've given it only one vector, but we've been able to plot this vector at different positions of the coordinate system. And that is the way that a physicist views a vector. It can be placed anywhere in the coordinate system, but its direction and magnitude is what defines it. Now, most of the times, we are going to assume the vectors are, if nothing else is expressed about them, they are going to be with their tail at the origin. So to summarize, our helper function plot vector receives two arguments, two lists, a list of vectors and a list of tails, and it plots this nice graphic of us to illuminate what the vector is. So let me stop for just 1 minute and give you a little exercise. So just create in a new list, just in a new, code cell, create your own list of vectors and create a list of tails and plot them at your will. Just let me give you 10 seconds to do that. If you have a problem, if you raise your hand, we can send help right away. Okay, I'm going to continue, and please feel free to use the written out narrated lesson to stop and catch up as you need to while we move along, because obviously everything is available there for you. Now, what we're going to do is define the fundamental vector operations, and these are two fundamental vector operations, the idea of addition and multiplication by a scalar, or scaling. And so let's visualize vector addition by defining two vectors. So here we have the mathematical representation of two vectors as an ordered list of numbers, and we're going to define them in our our open Jupyter Notebook as two variables. We're going to call one A. We're going to use NumPy array. So let's do A equals a NumPy array. And we're going to give it the coordinates. I'm going to feed a pair of coordinates -2, 1. That is A. I'm going to then define B as a NumPy array. And I'm going to give it coordinates 1, -3. And then I'm going to say, well, I'm going to define the origin as a NumPy array with the set of coordinates 0, 0. And then I'm going to define a list of vectors. The list of vectors is going to contain A, the vector we've just defined as a NumPy array, A, B, and A plus B. And we're going to plot A, B, and A plus B. To illustrate the idea of vector operation, where what you do is place the second vector with its tail at the head of the first, and then the addition will be the vector that has its tail at the origin and its head at the position where B arrives. So let's then, to plot this result, define a list of the tails where we want to plot each one of these vectors. So the first vector, A, we're going to plot with its tail at the origin. The second vector, B, because we're adding it to A, we're going to place its tail at the vector A. And then the final vector, which is the addition of a plus b is going to be plotted with its tail at the origin, right? So this is how we're going to illustrate the vector addition. We have now defined the vectors, the list of vectors and the list of tails that we want to plot. So let's use our helper function plot vector with the two arguments, vectors and tails. All right? So I execute this, and you can see here an illustration of what is happening. The vector A that we defined here, remember, minus 2, 1. The coordinates of the vector indicate how many places in the coordinate system it moves. The first dimension is the horizontal dimension. Of course, it moves minus 2 and 1. So here is the vector A. And then the vector B moves 1 square in the x direction and minus 3 in the y direction. So this guy, he's moving 1 to the right and minus 3 with its tail at the head of A. And then finally, A plus B is that result. So we are able to use this plotting function to help us visualize the result, because bear in mind, we have actually invoked here the vector addition that is built in Python. We are using the plotting to show us what happened, but we have relied on Python to actually do the addition for us. We are only then visualizing that result. Now, in this visualization of vector addition, you can see that the vector A plus B, which is the final vector we plotted here, ends up in the coordinates that result, you can see clearly from the figure here that the coordinates, the x-coordinate, for example, of A plus B is the result of adding the x-coordinates or the horizontal movement of vector A and vector B, while the vertical coordinates is the result of adding how much the vector A moves in the vertical direction and B moves in the vertical direction. So this visualization helps us understand that this sum is the same as adding the respective coordinates, how much each vector moves in the horizontal direction and in the vertical direction. So here we're doing, instead of defining it first in this way, we're visualizing it and then realizing that's what happens. Now, for scaling, let's define a new vector, like, for example, let's define C equals NumPy vector now with two coordinates 2, 1, NumPy dot array, and we give it the coordinates 2, 1. And now let's say that we're going to plot the vectors, our list of vectors that we're going to plot are the vector C and the vector 2 times C. And we're relying here on Python to actually do the multiplication, and we're going to plot the result, plot vectors. And our arguments are the list of vectors. If we don't give this function a list of tails, it assumes that all the vectors are plotted with their tail at the origin. And I've made the mistake of adding an S at the end of the function. So here we have the vector C that goes 2 in the horizontal, 1 in the vertical, and the vector 2C, essentially the scaling had the effect of multiplying the horizontal tail to head direction by 2 and the vertical tail to head direction by 2. All right, so what is the effect? Try it in a new cell. What is the effect of multiplying by a negative scalar? This is a little challenge to you, a little exercise. I won't say it. Let me give you a few seconds to just try it in a new cell and convince yourself that that makes sense to you. All right, I won't give you the answer, but you can discuss it with your neighbor as you need to. Let's now view a very important idea in linear algebra, that is the idea of basis vectors. Right, so Imagine any vector. Let's call this, imagine that this is a vector that is only horizontal. So the first coordinate, it has a value little u here. The second coordinate has a value 0 because it doesn't move vertically in any way. And you can always scale it by 1 over u so that it becomes, we know that's what scaling does, right? It becomes 1 over 0. Similarly, any vertical vector that you can imagine can be scaled to give us the vector 0, 1. Going the opposite way, if I can scale a horizontal vector to get 1, 0 and scale a vertical 0 to get 0, 1, then I can always create any horizontal vector from 1, 0, or I can create any vertical vector from 0, 1. And once I have a horizontal vector and a vertical vector, I can add them together to get any vector in space. So this is why these are called basis vectors, because we can generate all other vectors by adding scaled versions of them. So for any vector, its components really can be obtained by multiplying these basis vectors to generate it. So let's visualize this, because too many words just get us confused. Let's visualize this with Python. So what we're going to do is we're going to create what I've just called the basis vectors as NumPy arrays. So let me define I equals NumPy array, and I'm going to give it the coordinates 1, 0. I'm going to create J as a NumPy array 0, 1. So those are the ones, 0, 1. Those are the ones that I'm calling the basis vectors. Indeed, I could create another vector. Let's call it, well, I'm calling it vec as a linear combination. Well, I haven't defined that, but let's do a scaled version of I plus a scaled version of J. We saw scaling a moment ago. So now let's do a list of vectors. This list of vectors contains I. We're going to plot the I vector, the unit vector that we've just created. We're going to plot J. We're going to plot 3 times I, and we're going to plot 2 times J. And finally, we're going to plot this vector vec that we've just created. And so that's our list of vectors that we want to visualize. So plot vector is our function, and vectors is the list, and if we don't provide tails, it's going to plot them all with the tail at the origin. So it's hard to see, but we have the 1, 0 here, horizontal vector with length 1, the 0, 1 vector, the vertical vector with length 1 here. Then we have 3i over here. I don't know if you can follow. I wish I had a bigger cursor. And 2, the length 2 vertical vector, and then the addition in this way. So let's think about now that we have this idea that adding 2 vectors that were each multiplied by a scalar can sort of travel around on this in the plane. Let's use this idea. This is called a linear combination. So I'm going to escape M. So I don't have my, all right, so I'm going to leave a note here instead of pulling the other lesson, because this is important, that this is what we call a linear combination. The idea that we are adding together 2 vectors that were each scaled by a number, by a factor, by a scalar, multiplied by a scalar, just scaled. That's it. All right? That's the idea of a linear combination. So then we have another idea, that is the idea of span. It brings us to this idea that if I can make a linear combination of 2 vectors by adding scaled versions of them, then if I vary the scaling value and just make that bounce around different values, I can start getting all sorts of vectors out of that combination, and that's the idea of span, the set of all possible linear combinations. So let's do an exercise now to visualize this. So imagine that we already have our vectors I and j, the basis vectors that we define, but we're going to do a little bit of iteration here to create just a number of random vectors. So let's create first an empty list of vectors and with our square brackets, and we already have I and j, so we're going to use I and j to generate a bunch of other vectors from linear combinations of I and j. So let's do that in a for loop, and I'm not going to need to use the variable here, so I'm going to do for in range. And you can change this number. Let's do 30 to start with. And then I'm going to create m as a new vector that is a random, first I'm going to create just a random integer, rand int from minus 10 to 10. That's the options. I'm going to create another random integer, rand int, from minus 10 to 10. And then we're going to do vectors. We're going to just append to this empty list of vectors, append, and we're going to use m multiplied by I, so m times I, a scaled version of the horizontal unit vector, plus, I'm going to do a little space here, plus n times j. So as we complete this sequence here, we're going to just append 30 random linear combinations of I and j to this list. And now we can exit this and plot this list of vectors. Now, I encourage you to try with different values. Where's my error? Oh, I need to load the, where was... All right, we needed to load this. I'm doing a shortcut to rand int from NumPy. So we're going to do it now again. And we have a bunch of vectors pointing in every direction. And you can imagine now that if I just change this number to a bigger and bigger one, you can start getting the feel that really, for a big enough number of random vectors, you can travel all over the two-dimensional space. And that is the case, that is the idea of span. By making linear combinations of I and j, we can travel all over the two-dimensional plane. The span of I and j, indeed, is the whole two-dimensional plane, and that's why they're basis vectors. They can generate the whole space. Now, we also created before two vectors a and b. What would happen if we, instead of using I and j here, were to do the same exercise but with a and b? So here I'm going to cheat a little bit, copy and paste from the previous cell. We don't normally want to copy and paste. We want to pay attention to what we're doing. But in this case, I know that all I'm doing is I'm going to change in this line here m times a, n times b. I'm changing the vectors that I used to generate this sequence of vectors, and I'm going to plot it again. So I see now that indeed these vectors produce like a different sort of arrangement. They kind of have a preferred, they're more dense in one direction than another. But if I think about adding an infinite number of linear combinations, eventually I am going to be able to travel on the whole two-dimensional space with A and B as well as we did with I and J. So there's no reason that we had to choose I and J as the basis vectors. We could choose another set of basis vectors. A and B, in this fact, can still fill up the whole plane if we were to be able to construct an infinite set of linear combinations. Let's see another situation. Let's create D as numpy.array, and the vector here now is going to have the coordinates -1, comma, 0.5. So this is our new vector that we're going to try to play around with, okay? So I've created this new vector, minus 1, 0.5. And now what I'm going to do in this same process that we were using before, where I create a random linear combination of two vectors, I'm going to use A and D for this set. A and D, two vectors that I'm choosing now to create 30, 40 here random linear combinations. Let's look at that. That doesn't quite look like the previous case. It is not, certainly it doesn't seem like it is able to travel all over the two-dimensional plane. If we were to choose A and D to try to make linear combinations, we're kind of stuck. We are stuck in a line. We're not able to travel all over the space. And the reason for this is that, in fact, A and D are collinear. A and D, one is a multiple of the other. They live in the same line, which means that the span of A and D together is just one line. We are not able to travel all over the space with these. So if we go back to our notes here, we're going to the official definition of what a basis is to show for you. A basis for a vector space, in this case, the vector space we're talking about is 2D space, is a set of linearly independent vectors that span the space. Linearly independent, that's not what A and D are. They lie on the same line. They're collinear, and that means they're linearly dependent. So there's a key idea here that you need the two vectors to be in some way independent of each other, not be on the same span, not be on the same line, to be able to travel all over the plane in this case. Let me just double check here. All right. I encourage you to revisit the idea of basis afterwards. We also talk about a basis as a full set of independent vectors. So if we are in 2D plane, a full set will have two elements. If we're in 3D space, we need three basis vectors. That is what the idea of a full set. So I won't dwell into this because I really want to show you what a matrix is. For now, we've talked about vectors. We now want to talk about a matrix. Now, in many books, in many textbooks, what they will tell you when they define a matrix is that a matrix is like a table of numbers, right? Arranged in orders, in rows and columns. And maybe that's enough for most people. You can visualize a table of numbers arranged in rows and columns. But it is really important to get a feel for what a matrix can do, what it does, what it really means. So we're going to reuse our friendly vectors A and B. And in the previous little experiment, we create with 30 random linear combinations of A and B, we could visualize that they generate the whole space, the whole two-dimensional space. And we had the vector C that was 2 and 1. So I'm going to remind us here that we had I'm going to write it in bold for A and B. All right, we have these two vectors, and we know that we can write these two vectors as linear combinations of I and j, right? I and j being our unit vectors in the horizontal and vertical direction. Now, we also had a vector C. C was the vector with coordinates 2 and 2, 1. That's the coordinates of this vector. So we could write that as a linear combinations of I and j. So C, well, I'm just going to write it here. C is equal to 2 times math BFI plus, was it 2 and 1? Yes, 2 and 1. That is the linear combination of I and j that produces C. Those were, I'm going to remove that, those asterisks now because I don't like them. I'm just going to do a space here. All right, 2i plus 1j. So now imagine that we use the components of C, 2 and 1, to make a linear combination of A and B. Why not? Use the components of C to make a linear combination of, I'm going to cheat here, A and B. So we're going to do 2a plus 1b. 2 and 1 are the coordinates. If we do 2a plus 1b, you could do it in a little piece of paper. You know what a is, and you know what b is, but I am going to skip ahead a little bit and show it to you, and in the sake of time. Here's 2a plus 1b. A was minus 2, 1. B was 1 minus 3. So I can scale vector A by 2, scale, well, by 1, nothing happens, and then add the coordinates to get the result, minus 3, minus 1. This result is a new vector that we can call it C prime. It's a new vector that has the components 2 and 1 if we were to use A and B as basis vectors, because you see there's a linear combination of A and B multiplied by 2 and 1. So 2 and 1 could be the coordinates, the scaling factors that allow us to produce this vector from a linear combination of A and B. But the coordinates that allow us to make this vector from I and j are minus 3 and minus 1. So this vector, C prime, has components 2, 1 in the AB system, has components minus 3, minus 1 in the IJ system. Now, this is what's really interesting. If you arrange the vectors A and B as the columns of a matrix, if you arrange the vectors A and B as the columns of a matrix, minus 2, 1, 1, 1 minus 3 as a matrix, and you multiply that by the components 2, 1, you get minus 3, minus 1. So the matrix formed by putting A and B in the columns, when multiplied by the vector C, gives you C prime. Now, this is really the key idea, that by placing two vectors as columns, we've created a matrix. And this matrix is a way to transform from vector C to C prime, or from any vector to another vector that represents going to another space. All right, so now let's do this computationally. Let's play with this a little bit computational. The key idea here is that the matrix A that we formed by placing two vectors as columns represents transforming from one space to another space, the space of AB to the space of IJ. Those spaces are, well, they're both two-dimensional spaces, but they're different. Right, so let's create A, capital A for a matrix. We use capital A. We're going to do it this way. I'm just going to do a list of lists minus 2, comma 1. Those are the components of vector A, comma 1 minus 3. So that's A, a list of lists. That's what we're going to create. But we're going to turn that into a NumPy array. Okay, and then we're going to just print it out just to look at it. And so there we see minus 2, 1, and 1 minus 3, which is what we wanted. And let me remind you that minus 2, 1 is the vector A, 1 minus 3 is the vector B. So we created a matrix with A and B as columns. All right. Now, we can use the NumPy dot function to multiply this matrix times the vector. So I could say C is a vector we've already defined. Let me print C. We already have C, okay? And now we're going to use the NumPy dot to do a function to multiply a matrix, times this vector C. And out comes C prime. C prime, the vector C prime that we created by making a linear combination of A and B with the original coordinates of C. Okay, so we could also do a multiplication of A times, we're using the built-in function from NumPy to make a multiplication of the matrix times a vector, and I'm going to multiply it now by the basis vector I, and execute that, and out comes, well, that's funny, minus 2, 1 is actually the same as A. And if I do A dot, the multiplication with the matrix A times J, the other basis vector, out comes 1 minus 3. So that's kind of interesting. These are the vectors A and B. If I multiply the matrix, again, multiply the matrix by the vector I get A. If I multiply the matrix by the vector J, I get B. So the matrix, so remember that we use the components of the vector C in a linear combination of A and B to get C prime. And A and B in that sense became like the basis of this new space where C prime lives. Well, what we find now is that the matrix represented, the matrix A, formed by the columns, by the vectors A and B as columns, represents a linear transformation that takes the basis vector I to A and the basis vector J to B. So by knowing what a linear transformation does to the basis vectors I and J, we know exactly what it does to all the vectors. Now we have a pretty neat helper function called plot linear transformation. And we give it a matrix, and it will plot the space, two-dimensional space, a plane, with the unit vectors I and J drawn here on the left, and the space now transformed into this new plane where we have A and B as the unit vectors. We've drawn in this plot a grid to represent the intersections of the grid, give you an idea that there's a point there that represents a vector. So every point, now, as you saw before, when we were drawing 30 random vectors, the drawing gets pretty messy, and we could do 30, 50, 60. We got the idea that with these two vectors we could fill the whole space, but it gets pretty messy. So from now on, we imagine the space as this grid of points where every point represents a vector that we're just drawing its head as a point, okay? So in this case, in the left, every point on this plane, every intersection of two grid lines represents a vector that lands there, the head lands there, and that vector in the right, after being multiplied by the matrix A, will have landed in a different position. It's transformed. The whole space gets transformed by matrix vector multiplication. So one key idea of a linear transformation that we haven't, we're not going to prove, but I'm stating here, is that for a transformation to be linear, we require that the origin remain in the origin at the same location. So the matrix multiplied by 0, 0 should still give you 0, 0. And that all straight lines land on also straight lines. So if any transformation that turns a straight line into a curved line is not linear, and in fact, the distance between the lines has to be kept uniform. So that is what we require for the transformation to be called linear transformation. Now let's practice with a different matrix. Let's define now M we're going to try a matrix that is, let me show you the matrix here first, and then I'm going to create it. The matrix here, it is 1, 2, and 2, 1. That's the matrix we're going to work with right now, 1, 2, 2, 1. The meaning of this matrix is that by the linear transformation that this matrix represents, the unit vector I, 1, 0, lands on its first column, 1, 2. The unit vector j, 0, 1, lands on its second column, 1, 2. So we know what this linear transformation does to the unit vectors. The first column represents where I lands. The second column represents where j lands. All right, we're going to create it. And, well, remember that also I and j are the basis vectors. And so any vector x can be represented as a linear combination of I and j. I know where I lands, I know where j lands by this linear transformation, so I can use those two new vectors as a linear combination with the x and y coordinates to know where any vector x lands in the new space, produced by multiplying the matrix times the vector. So let's play around with this a little bit. Let's create M as a, it's going to be an NumPy array, but I'm going to start with a list of lists. And so let's do 1, 2, and 2, 1. Let's do M equals NumPy array of M, and then let's print it out. And here it is, 1, 2, 2, 1. That's our matrix M. So if I do M dot I, you can predict what's going to happen, right? It's going to go to the first column of M, 1, 2. If I do M dot J, you can predict what's going to happen. It's going to land on the second column, 2, 1. All right, so let's now look at that linear transformation using our helper function plot linear transformation with M. And you can see the vector I and j, and on the right-hand side, the vector 1, 2, which is where I lands, and the vector 2, 1, which is where j lands. To see what the transformation does to a particular vector, we could use our vector plotting helper. For example, let's do x equals NumPy. You can create any vector you want. I've created one with 0, 0.1, 0.5, 1. And I'm going to make a list vectors with x and m dot x. And then I'm going to use our helper plot vector and with this list of vectors, and I could see what happened to this vector. Originally, it was here, 0.51, and then after the transformation, it lands over there. And I could see now, for any vector, what happens to it. Now, here's a point of something to notice. And when you represent a matrix in Python, in particular, we define the matrix by listing first the rows. But in our point of view here in the discussion, we're always talking about the columns first. Now, you didn't notice that, and when we didn't emphasize it before, because I was cheating a little bit, and I was using an example matrix that has the same list of rows as the list of columns. And so I didn't have to point out to you that actually 1, 2 is the row, and 2, 1 is the second row. That, I just didn't want to drag it along, but now I have to tell you, because if we want to do a different matrix, say n equals NumPy dot array, let's create it right away as a NumPy array, and I'm going to do here a list of, let's say, 1, 2, minus 1 comma 2 again, and I'm going to print n. Then you can confirm that indeed the first component here was the first row. Okay, so we create the list in Python using a NumPy array by giving the list of rows, but we are usually thinking about the columns when we see the matrix as a linear transformation, because the first column of that matrix is where I lands, the second column is where J lands, and that explains everything that the matrix does. Let's now plot the linear transformation with n. And we have here the effect of n on many points in the grid. So let me stop here for just one little bit and ask you to create a 2 by 2 matrix of your choosing, and as an NumPy array, then print it, and then plot the linear transformation just like that. Or perhaps you can just change the numbers here and try a couple of different values. Just take 5 seconds to try different values with your example. We'll take a break in about 10 minutes or so, 15 minutes. A short break. If at any point you have a question, Ting is here. Juan stepped out. Oh, he's over there. Okay.
We should watch the videos. I think the videos are really awesome.
Yeah, I recommend it very highly. But let me give you a word of warning. When you watch a video lecture, it has the same effect as a lecture. They're very beautiful, they're very inspiring, but you get a sense of false confidence that you've understood the concepts. I believe that when we use Python, when we manipulate these ideas in different ways, then you get a different level of understanding because you're actually playing around with them. It helps to take notes, of course. That's another way of playing around with the ideas. But using computing is another powerful way to bring the ideas to life. So, yeah. Of course. Of course. Okay. Now, let me now explain matrix multiplication. So this is our next topic. Consider again the matrix that we defined in the beginning of this lesson, which had the vectors A and B as columns. We know that the first column is where I lands on the transformation, and the second column is where J lands after the transformation. So multiplying the, applying the linear transformation is the same as multiplying the matrix times the vector. So this is a very important result, that applying the matrix A times a vector is the same as making a linear combination of the columns, remember A and B were the columns, making a linear combination of the columns scaled by the vector coordinates. So here is shown in mathematical notation, x is a arbitrary vector with coordinates x and y, and we know that by multiplying it with the matrix A, we're going to get the first coordinate x multiplying the first column, and the second coordinate y multiplying the second column. This is, in fact, how we built it. So the matrix vector multiplication is a linear combination of the columns of A scaled by the components of X. That is a key idea that is much easier to use than the rote formulas that you learn in a typical linear algebra class. And this also generalizes to higher dimensions. So in 3 dimensions, suppose that we have a vector in 3 dimensions that has 3 coordinates x, y, z. And we have a matrix B that represents a linear transformation between 2 spaces, two vector spaces. So making the multiplication of the matrix B times the vector Y is a linear combination of the columns. So in the first column of B is 1, 2, 0. Here's the vector 1, 2, 0, multiplying by the first component of X. The second column multiplying the second component, and the third column multiplying the third component. And now what you have is the scaling of three vectors added together. The result is, of course, another vector. The result of a matrix vector multiplication is a vector. So let's now play with some special transformations. Because we know that the columns of the matrix is where I lands and J lands, then we can actually think through some special transformations in our head. So imagine a transformation that takes the plane and rotates the whole thing by 90 degrees. So the vector that is the I vector has to go point down, and let me do the positive 90 degrees first. So we have the vector, imagine the vector that is horizontal, ij, this way, and it has to rotate 90 degrees. It'll go to where the vector j was, which is 1, 0. So from 0, 1 to 1, 0 by rotating 90 degrees. The vector that was at 1, 0 rotates down to minus 1, 0. So we immediately know where I goes and where j goes. I from 1, 0 goes to 0, 1. You can draw this picture in a piece of paper. J from being vertical goes to the negative horizontal. So we can build immediately the matrix that produces a rotation of 90 degrees by placing those two columns together as a matrix. The rotation matrix is not, you never have to remember a rotation matrix. We'll see a rotation by any angle in a little later. But you don't have to remember, you just have to work around and work it out in a piece of paper where each one of the basis vectors lands after the transformation. So this R is a rotation. Let's create it and let's look what happens. All right, so let's create R. We're going to call, no, I didn't want to do that. I'm just going to create a new cell here. Let's call it rotation. And that rotation is going to be an NumPy array. And remember, in Python, that's why I had to tell you now we have to list the rows to create the array. So let me show here, even though we think in columns, Python needs us to talk to it in rows. So 0 minus 1 is going to be the first row. And the second row, 1, 0. Let's print it to make sure that we're getting what we wanted. And indeed, here is the first column. Now we can check mentally that this is correct. The first column represents where the vector I lands. Yeah, it comes from horizontal, it went to vertical. And the second column represents where j lands. That makes sense. Now we can use plot, linear transformation with rotation to visualize it and see that it is indeed what we were expecting. So that is a special transformation. Another special transformation is what's called shear. A shear means that things kind of shift, in the horizontal, perhaps, direction. So the feature of a shear transformation is that I, the horizontal vector, just stays where it was, but j, the vertical vector, is going to get slanted out. So for example, it can go from 0, 1, the vertical direction, to 1, 1, the perfect diagonal. That is a shear. We know where I lands, it stays the same. We know where j lands, it goes to 1, 1. We can write the matrix. The matrix S is first column where I land, second column where I land. So now we can write it in Python, and Python wants me to talk to it in rows. So shear equals numpy.array, and I'm going to create, 1, 1, and 0, 1. Let's see if we got it right. and double check with our notes, and it is correct. And now let's plot linear transformation with shear and see what happens. And that is the effect of that transformation. The shear transformation just makes things slanted. Another special transformation is called a scaling. It actually doesn't do anything else with the vectors I and j than scale them. So maybe it will take I, for example, to the value multiplied by 2, that's one possibility, and take the vector j multiplied by 1/2, that's another possibility. That is a scaling, doesn't rotate or shear the basis vector, it just scales them. So let's create that. The scaling, it takes let's look at it. We can create the matrix, remember, by putting those two vectors as columns, but we have to write them as rows in Python. So 2, 0, 0, 0.5. Let's print it to make sure, sanity check. Is an error here with parentheses. There we are. And it is what we wanted. Let's double check. 20005, that's correct. And now plot linear transformation with this scaling matrix. And you can see that the I and j vectors only got scaled, and the vertical lines remain vertical, horizontal lines remain horizontal, but everything got stretched in one direction. Now, a special scaling matrix leaves both vectors in the same space, in the same length. That's a special one, and that's called the identity matrix. Okay? So if we multiply by the identity matrix, everything stays exactly the same. Now, let me give you a little challenge, and then we do matrix multiplication, and then after that, we can take a break. The little challenge that I want to take you is for you to actually create a rotation matrix that rotates every vector 90 degrees the opposite direction. We created something that rotates counterclockwise. Now you create a matrix that rotates 90 degrees clockwise. And plot it and make sure that it makes sense to you. Just think, where do the unit vectors land? And you can write that columns, those two columns, hopefully. If you have any issues, let us know. Normally, Juan, when we have an exercise like this, if I was on Slack, I would create a little comment on Slack that says, "Are you finished?" And then put a green check mark as reaction, and people could just click on the green check mark. And when we have enough green check marks, we can move on. That's a neat idea. So you can start the reactions with a green check mark so everybody clicks on the same reaction. All right, we'll take a break after this next topic, which is matrix multiplication. So if you have a question, we can discuss it. Then we'll take a 5-minute break, okay? Now, what do you think happens when we apply two linear transformations, one after the other? So for example, suppose that we rotate all the vectors by 90 degrees, and then we apply a shear transformation after that. Well, to take any vector x, you rotate it by multiplying by the vector that we created called rotation, or in our notes is what's called R. Multiply by the matrix R, and every vector gets rotated. Now take the output of that transformation, take all of the vectors in the transformed, rotated space, and apply shear to those vectors, and that's what we get with the two transformations one after the other. So imagine that we take the output of Rx, that's a vector, and then we want to shear them. Well, that's another matrix vector multiplication, multiplied by the scaling we called shear that we called S. So essentially, applying two linear transformations one after the other is the same effect as composition of transformations, which mathematically is matrix-matrix multiplication. So here, R multiplies X, the result of that is a vector, and then we multiply by S. That is the composition of two linear transformations, which leads to matrix-matrix multiplication. Now, we can almost work this out in our heads, because we know that the unit vector I gets first rotated to 0, 1, which is the first column of R, and then it gets transformed by S via the multiplication S times that output. So we can almost work S times 0, 1, which is where I landed after R transformation. We can do that as this is matrix vector multiplication. So it's a linear combination of the columns scaled by the vector components. So the components are 0 and 1, 0 and 1. The vectors of S are 1, 0, 1, 1. And we can kind of do that on a piece of paper quite quickly. So we can almost do this whole thing, this matrix-matrix multiplication in our heads. But what we can do also in Python is use the matrix-matrix multiplication. So if we do print shear, the matrix-matrix multiplication in Python is the @ operator. Print shear times rotation, that is the output of the matrix-matrix multiplication. The meaning of the matrix-matrix multiplication is that we applied the matrix on the right first. This matrix that is on the right is applied to the vector first, and then by a composition of transformations, we apply the second one. So let's look at the combination of these two with our plot linear transformation. Shear matrix vector matrix multiplication with Python, and that is the output. The rotation plus the shear together is composition of two linear transformation, which is the same as applying the two transformations in sequence, leading to matrix-matrix multiplication. And that is a key idea, that matrix-matrix multiplication corresponds to two transformations applied in sequence. Now, this is actually an idea that can save you from so much memorization and from so much needless computations on pen and paper. It really illuminates the properties of matrices. For example, if we so is it the same to apply shear and then rotate? Is it the same to what we just did? Well, let's see what the result would be. Plot linear transformation. And then now we're going to do rotation, shear. So we apply the shear first to the vectors, then we apply rotation. What do we get? Well, it doesn't look that we get the same thing. So this idea illustrates that matrix multiplication is not commutative. A times B as matrices is not the same as B times A, because the order that we apply the transformations does affect how the space gets transformed. So SR is not the same as RS. By the way, our plotting function allows you to enter two matrices to see two transformations in sequence. So we could do plot linear transformation shear, comma, rotation, and rotation, comma, shear. And let's look at that. So shear and rotation. What's my mistake? Oh, an S, yes. Here, we have applied, this is before the transformation, then we apply shear, and then we apply rotation in sequence. It's going to be awkward for me to show it here, so if you follow along, you can see it on your own screen, because it's hard to show everything in the screen with the projector. And now what we're looking at is the different order of those transformations, and you can see that the result, this one here, is different than this one here. Applying the two linear transformations in sequence is not the same if you change the order, because and matrix multiplications is not commutative. Now, this gives us a sense of what the meaning of the inverse matrix might be. If I were to apply shear and then find a linear transformation that turns everything back to where it was, then that linear transformation is it undoes everything that the shear matrix did, and it is indeed the inverse matrix. The matrix that does that is the inverse of S. A matrix that undoes, I guess, the effect, the linear transformation of another is its inverse. And here we're going to take a break after this. In Python, the inverse we're going to do it with NumPy.linalg, the linear algebra submodule, and we're just going to import this one function, inv. And then we can do, we have already, what's the matrix M? Let me see, M? Okay, we already have this matrix M. So now we're going to compute M inverse, and that's going to be the inverse. Python gives us the opportunity to get the inverse, and we can now plot the linear transformation. These are two transformations, so I think I misspoke before. It's not the same function. It's a different function that receives two transformations and plots the sequence. So I'm going to plot the sequence of transformations M and M inverse. So M, that's the effect of M. We've seen it before. And then we apply M inverse, and where do we land? Right where we started. That's the effect of the inverse transformation. So let's take a break now. The combined action with this idea of inverse matrices, the combined action of M and M inverse is, of course, that nothing happened, which is the same as the identity matrix. The identity transformation is the one that does nothing. So that is how we can understand this concept of the inverse of a matrix, that multiplied by the matrix is equal to the identity. So this is our first lesson. This is, we've covered a long stretch of concepts in a hopefully intuitive way. Let's take a 5-minute break and come back for lesson 2. Thank you. I'm going to need some agua. All right, ready for lesson 2, everybody? Let me go back here. Thank you to Juan for telling me how to make the cursor larger. And we're starting lesson 2. Lesson 2, I'm going to pull up here the MB Viewer version of it, is all about the matrix, the matrices. We're going to focus now on different ways to looking at matrices. We start by revisiting the idea of a matrix as a linear transformation. And we're going to expand this idea with 3 different points of view, with different perspectives on what matrices do. We started by a silly quote from the movie The Matrix, and most people in the room might not have seen it because it is actually 30 years old. No, 20? 20 years old? Ah, okay, I'm off by a decade. No? Okay, 20 years old. Yeah, okay. Right, okay, got it. All right. It's old. It's, yeah, you have to see it as a now a vintage piece, right? Yeah. Anyway, I liked it. I saw it millions of times. I could watch it again, probably. All right. So now let's do the following. Let's save this. I'm actually going to do the following. I'm going to merge these cells, copy all this content, and I'm going to, well, let me just make sure that it's saved. No, I don't want that. Well, just close and hold. So what do I do for it to save? See, I need my toolbar. Now I can do that. Okay. And now it's close and hold. And I'm going to create a new lesson now, a new clean notebook to start with, playing around. And I'm going to paste that initial code that we need for loading our libraries and loading the helper functions. And let me create a new cell here. I move it up and just leave here a note that this is going to be my lesson 2 or live lesson 2, whatever you want to call it. And we're going to start a brand new Jupyter Notebook here for this lesson. And we start by loading the NumPy matplotlib. Yes, we're going to do matplotlib notebook here. Yes, okay. So instead of matplotlib inline, we're going to do notebook for this lesson only, because we're going to take advantage of the interactive figures for this lesson. So change just that bit here and?
So we have to actually restart. The backend cannot be swapped.
I have to restart? But it's a new notebook. And I close the other one. Okay. Yeah, I know that's something mysterious. So I need to restart. So even if you move to from one notebook to another notebook, the back end is connected to that. Oh, okay. Matplotlib mysteries. I think it's a new notebook, it's a different kernel, right? Ah, I may have. Yes. Okay. Good. We already discussed that a matrix is a linear transformation, and let's now start with an example matrix here. So I'm going to pull up the matrix that we're going to work with here. It's this matrix over here. If you see a matrix like that, now we know that the meaning of this matrix is that the first column is where the vector I lands after the transformation. The second column is where the vector j lands after the transformation. So we know what this matrix does. So let's visualize it with our helper function. So let's first define it. A is a NumPy array. And remember, we have to enter the rows for Python. That's the first dimension in Python, 1, 1. I think I need an extra parenthesis here, square brackets, comma, -1, 1. All right, so those are our two rows. Let me just print it out to make sure that we have what we expect. And here it is. That's our matrix. Let's plot the linear transformation corresponding to this matrix. And unfortunately, with the large screen, I can scroll sideways. Okay, that's not, because I've made the Jupyter Notebook so large. How can we?
Turn on the notebook to activate the notebook mode. Just can you check that one?
I'm not following you. So is it because of the size of my notebook?
Yeah, so you have to type the extra 3 line in order to shrink the size to get it rendered correctly.
Okay, we have some extra lines here to get, okay, because we are in the notebook mode. Okay, so I'm going to go back to our lesson, print it out, because I have forgotten that for the second lesson, we have some extra lines here to configure the helper functions that we have for the option of the interactive matplotlib figures, which changes the size of the output. Okay, so this is just a different configuration that I have to apply for our helper functions. For notebook equals true, which changes the sizes of the output. This is a technical detail that we, it still doesn't work. Do I need to restart the kernel? All right, there we are. Okay, so as you can see, we're getting the interactive figures now. For the two-dimensional plots, it's not going to help us very much. You feel free to just hit the stop button here for these figures as we go along, because we're really going to exploit the three-dimensional. Do you need some help? Okay, Juan, over here. This guy. We're really going to exploit the interactive mode of the figures for the 3D case. But we have to use the same mode for the whole notebooks as far as we know, and so that's why we have to start with the 2D figures as well. All right, so let's create now our basis vectors. We're going to use them, I equals NumPy dot array, and it's just one list of numbers here, 1, 0, j equals NumPy dot array, 0, 1. Here are our basis vectors. The matrix that we've created right here has two columns. The columns are 1, -1, and then 1, 1. Let's create two vectors that represent the columns. So let's create A as the first column of this matrix, 1, -1. Let's create B as NumPy dot array, the second column, 1, 1. One small parenthesis here to note that, well, we know that A represents where I land. So if I were to do a vectors equals a list I, A, I can plot vector with this list. And you can see here in my plot, you can barely see it, but now we have a larger cursor at least. That is the vector I, and that is where I landed after the linear transformation, the column, the first column of our matrix. Now, if I were to ask you, well, the vector I has unit length. We know that. We can see it also in the figure because it's horizontal, so we can easily see it, that its length is 1. It's a unit vector. If I were to ask you what is the magnitude of A, then we could imagine drawing a triangle here and computing the length of A by using the Pythagorean theorem. That is the meaning of the norm of a vector, the length of this arrow that we've drawn here. And we could compute this because each of the sides is equal to 1. So 1 squared plus 1 squared, take the whole square root of that, and we get square root of 2. That would be the length of this vector. That has a meaning in linear algebra. The meaning is the norm of the vector. And we will use this in the rest of the lesson, so we introduce this definition here. The Euclidean norm of a 2D vector, its length or its magnitude is the square root of the square of its two components, and this also generalizes to higher dimensions. In Python, we have a function to compute this from the linear submodule, so we can compute the norm of this vector by doing NumPy dot linalg. Well, what will happen if I do it with, for example, I? What do you expect to happen there? It should give me 1, because that is a unit vector. If I try it with A, it gives me 1.4 and a lot of other things, which is actually the square root of 2. We can check that, NumPy square root of 2, and it is the same number. That is the norm of A. Okay, so after the transformation, the two unit vectors got scaled by square root of 2, and each box in the transformed grid will have length square root of 2. So now consider any vector in the plane, a vector, arbitrary vector x comma y. X comma y. As we saw in the first lesson, then the matrix vector multiplication A times X is a linear combination of the columns of that matrix scaled by the coordinates X and Y. Let's plot the linear transformation. And you can see in the plot that A has the effect of rotating the whole plane. It looks like negative 45 degrees, and it scales every vector, it seems, by this number square root of 2. We can see what the effect of A is. At the end of the previous session, we learned also that the inverse of a matrix would undo this effect, so it would have to shrink all the vectors by 1 over square root of 2, and then rotate the whole space by plus 45 degrees. We can imagine in our heads what the inverse has to do. But let's look at it. So let's create a new Python variable a_inv, and that's going to be the output of applying NumPy dot linalg inverse to A, and then let's plot the linear transformation with this new matrix and see what it does. And sure enough, it's rotating the whole plane by now plus 45 degrees and shrinking all the vectors by a factor. We can't see from the image what the factor is, but we are confident in our arguments, and that factor is indeed square root 1 over square root of 2. Now we could plot them both in sequence. Plot linear transformations. The S there is very important because we're plotting 2, and this is indeed a different function. And we're going to plot A and A inverse in sequence. And you see here before the transformation, here is our regular grid. It gets rotated and stretched, and then by the inverse, it gets sent back to where it started. Okay, I want to make a note that in the previous lesson, we did one line from NumPy linalg import INV, and we were able to use INV shorthand. And here we didn't do that. We used the whole long form of INV. The inverse is preloaded and available to us. And in the previous case, we were just using that for convenience to type a little less, but it was already available to us. So we're visualizing the effect of the two linear transformations in sequence. And also we have this idea that one transformation stretched the vectors and rotate them in the negative 45 degree angle, and the opposite one rotated everything in the positive 45 degree angle and shrunk all the vectors. And that is the effect of the inverse. So, okay. Now let's create the following matrix. And this is an exercise for you to do with this matrix right here. So let's give you just a few, a minute to do the same exploration we just did with the matrix A, but with this matrix B. You can create the matrix as an NumPy array, visualize it, compute the inverse, visualize it, and then compute them both in sequence, and see if you find anything special. We're going to leave you with this for you to continue exploring after the tutorial, because it's a very interesting topic, and I want to leave you with some curiosity. B is equal to B inverse. This is a very special matrix. These are used in cryptography. In fact, were the first applications of linear algebra to cryptography way back when, in the beginning of that field. Today they're not, because you can turn a message in text into numbers and then apply B, and then you can apply B again to untangle the code, and that was one of the first applications of linear algebra. So that can give you a little rabbit hole of Googling about for the evening. Very interesting. So let's now move to the next way of looking at a matrix. There's something very interesting that a matrix can do that is going to help us understand some things. We're going to work with the matrix C. Now, let me define it. NumPy array. And it is the matrix 2, 1 in the first row, 1, 2. And let's print C, and then let's also plot the linear transformation. With C. Error. Typo? Oh, extra square brackets. Yeah, okay, thank you. I've done that a couple of times. All right. We've played around with this matrix before. We called it different. Now we have it again. So we know by our previous discussion that the unit vector I lands on the first column, which is 2, 1, and we see it right here in the visualization. And so we're going to now visualize the effect of this matrix by applying it as a transformation to a whole lot of vectors of unit length, but which are form around a unit circle. So we're going to create an array of vectors of unit length going around the unit circle. So let's create an array of angles. Alpha equals, so we're going to do numpy dot linspace to create an array from 0 to 2 pi, and let's do 41 of those numbers. That's going to be a set of angles, and now we're going to create vectors. We're going to create vectors with as coordinates the cosine and sine of this angle, so that our vectors are going around the circle. Now here we're going to use a very nifty Python tool that is called a zip function. So we can zip together the cosine and sine to make pairs of them into coordinate pairs for forming our vectors. This is this is just, Python is so pleasant. List, we're going to create a list first, and we're going to use this magic zip thing with, as arguments, we're going to use numpy dot cosine of alpha, and then the other one is going to be numpy sine of alpha. So you see what we're doing here? We're taking cosine alpha, sine alpha, then zipping those together into pairs, and that's going to be our list of vectors. So now we have this list of vectors. We're going to do plot vector with this list of vectors, and sure enough, here's our list of vectors going around the unit circle. 41 of them, in fact. You can try different values. I recommend an odd value, so you get a vector on the horizontal axis and a vector on the vertical axis as well. So what is the first vector here in our set? Well, the first one, vectors 0, is the unit vector, horizontal, in the positive x direction. If we want to see the effect of the matrix C on all these vectors, well, if I want to see the effect on the matrix, on the unit vector I could do C dot with, well, I think I need a NumPy array to do this multiplication here. So let's turn into a NumPy array vectors 0, which is the unit vector, and out comes the transformed version of that vector. There are different ways of doing this. We're going to do it the long way. Just to be explicit, we're going to transform every vector in this list and append the transformed vector to a new list. Let me call that new vectors. We're going to create an empty list to start with, and then I'm going to iterate for I in range the length of this list of vectors. And we're going to just append new vectors dot append. What are we going to append in here? The product of the matrix C dot with the vector, original vector. And let's do, we need to turn that into an NumPy array because we're just saved it as a list. So vectors is our list, and I is the index. We're taking each one of those vectors around the unit circle, multiplying it by C, appending it to a new list, and now we can plot vectors with the new vectors. And I have a error, and here it is. That's very neat. Our vectors whose coordinates were in the unit circles, whose heads landed on the unit circle, got transformed to now trace an ellipse. An ellipse that, well, it looks like its semi-major axis could be around, it looks like it's pretty well aligned with the 45-degree line. And so let's see what the length of that semi-major axis is. We're going to do it the long way as well. There are other ways to do this. And so let's create a list of lengths to compute the length of every vector, and using the NumPy norm for I in range, again, len vectors. No, new vectors, well, they're the same, but just to be consistent. And we're just going to append to this list the numpy.linalg.norm of what? New vectors I. So we have now a list of all the norms of these vectors, the new vectors, and we could get the semi-major, we're going to call it semi-major, this is a new Python variable we're defining now as the maximum of all these lengths. Do you use an S? Yes. Let's print semi-major, and it looks like it's 3. We could do the same for the semi-minor as the minimum. Semi-minor is equal to the minimum value of the lengths. And let's print semi-minor. And out comes a 1. So the semi-minor axis here seems like it stayed at 1. And one of the directions got stretched into a length of 3. All right. So now let's look at one of those vectors along the semi-major axis. Its magnitude is 3, we know, and its direction looks like it's 45-degree angles from the horizontal. So it means that the horizontal component and the vertical components are the same. And we don't have the coordinates of this vector yet. We just have the length and the direction. But since we know it's 45-degree angles, we can compute each components, which are equal, as semi-major over NumPy dot square root of 2, the cosine and sine of 45-degree angles. And that is, in fact, the value of each coordinate of this vector, the longest vector here. So let's create a vector with these coordinates. We're going to call it u. u1 in fact, we're going to create a vector with these coordinates, and we're going to also create a vector that is in the original space and who got transformed into this vector after multiplying by c. So let's do u1. That is going to be the vector at the semi-major axis of the ellipse. So we're going to create numpy.array with the two coordinates are going to be, we have semi-major. Well, I could save this as, let me save this as, well, S is good. So I'm going to do, that is the length. So I can do, well, this is going to be S comma S. Let's print U1. S is not defined. Oh, let's re-execute that. Okay, that looks good. That is a square, the semi-major length divided by square root of 2. That's the x coordinate and the y coordinates, which are equal for this one vector that is lying here, the longest vector in the positive quadrant for this transformed space. Okay, let's just now. How do we find the vector on the original space that landed there by the transformation? Think for a bit. Very good. So let's do that. Let's compute the inverse. C inverse is going to be numpy.linalg inverse of C. And V, let's call it V1, is the vector that got transformed into U1. That's going to be equal to C inverse times C inverse dot U1. All right. That's the vector that gets transformed by C into U1. Let's see, plot. Let's just sanity check with our plotting facilities here. Plot vector. We're going to plot U. Do I need to give it a list here? Well, I'm not quite sure. V1. Yes, I need to give it a list. Okay, U1, V1. And here we see U1, the vector. It's a unit vector because all our original vectors were unit vectors. It's the unit vector that is in the 45-degree angle, it looks like. V1 is the transformed version. It's the longest vector in the ellipse. This is the one in the semi-major. So that's kind of funny because they're collinear. The vector V1 that got transformed by the matrix C into U1, the semi-major axis, the semi-major of the ellipse, is on the same 45-degree angle. So the effect of C on this vector, this unit vector on the 45-degree angle here, the effect of C on this vector was just to scale it. Well, it's a special vector. The scaling factor, we know it's 3 because we computed the length of that semi-major axis, and it's 3. The original vector was 1. The scaling factor is 3. So let's put a little note here because this is important. The vector that landed on the semi-major axis was only scaled by the effect of C. Okay, sorry, I need to do that. Much better. Okay, the effect of the matrix C on this vector is just to scale it. In fact, this vector is special, so we can write that as an equation here. C multiplied by this vector that we called V1, the effect of the matrix C by matrix vector multiplication being applied to V1 is to just scale it. So it is a scalar multiplied by itself, math BF V1 for our beautiful math equation where you, yep, thank you. Okay, so this represents this idea. Apply the matrix C to V1, and all you get on the other side is V1 scaled by a factor. We know the factor is 3, but that is a very special effect. Now let's look at the vectors along the semi-minor axis. We're going to pick the one pointing right and down to repeat this process. So let's compute now a vector which is in the semi-minor axis pointing right and down. Call it U2. I'm going to call it U2. It is a NumPy dot array, and now the semi-minor length divided by square root of 2 is the length of that component, comma, semi-minor. I think I need a negative side, semi-minor square root of 2, and this is right and down, so then this one is the minus. Let's print it, see if it, error, square root is not, also NumPy dot square root. Okay, that seems about right. It is 1 over square root of 2, the length, and it's pointing right and down. That's the unit vector, which, well, let's find that is the transformed vector that ends in the semi-minor axis of the ellipse. What is the vector that was transformed into it? The vector that landed there after the transformation. We can do that again with the inverse. So V2 is the vector that lands there after the transformation. So it's C inverse times U2. Print V2. And it's the same. Well, it's the same vector, it's in the same direction, it's the same length, which is to say it got scaled by a scaling factor of 1. So now let's plot vector U2, I need a list, U2, V2. The input argument to plot vector is a list of vectors. And here it is. Whoop, I think I have a mistake here. It's V2. There. Okay. It's just one vector because it's the same vector repeated. It falls on itself, scaled by 1. So it is a special vector. Well, let's look at the norm. NumPy dot linalg norm of U2. And it's 1, essentially. It's 1. So the effect of the matrix on the vector is just to scale it, again, but the scaling factor is 1. These vectors, V1 and V2, that are aligned with the semi-major and semi-minor axis of the ellipse are very special. The effect of the matrix is just to scale them. They're the eigenvectors of the matrix C. And this is a key idea. Often, students of linear algebra, when asked what an eigenvector is, are able to write an equation for the eigenvector, but are not able to say to you what happens to the eigenvector under the effect of the matrix, which is the important thing to know. The effect of the matrix on the eigenvector is just to scale it. They never get thrown off their span. So these are the key ideas. A 2D matrix transforms a unit circle to an ellipse. In this case, or at least our unit, the matrices we're looking at the moment. The vector that doesn't change directions after linear transformation is an eigenvector of the matrix. That is our second point of view of matrices. Our third point of view of matrices is going to be to look at them as creating a linear system of equations. Because for any matrix, for any vector C in the transform space, we just did it with two vectors, right? With U2 and U1, we asked ourselves which vector landed there, and we computed the inverse. For any vector in the space, we can ask ourselves what vector did it come from before the transformation? That is, we'd like to find a vector x such that a multiplied by x gives us this vector in the transformed space. So if we were to take, for example, the vector 1, 5 and the components of x as x, comma, y, what we're asking is, remember, matrix vector multiplication is a linear combination of the columns scaled by the components of the vector. So ax is x times the first column plus y times the second column. And if we were to have a right-hand side vector, say C, 1, 5, we're asking what linear combination of this form produces 1 and 5. This is the same as if we were to look at this on a row-by-row now approach. If I were to actually multiply out by x on the first term and multiply out by y on the second term here, and then stack those together into two equations for the first coordinate of the right-hand side and the second coordinate of the right-hand side, you see that we get two equations for the components x and y. So this is a linear system of two equations, and what we're asking by solving this system of two linear equations is what vector in the untransformed space landed there on the right-hand side by the transformation. We already know how to answer it by means of the inverse transformation with the dot product. So we can do that. For example, let's do it with a vector C. I'm going to, I wonder if I do that, will it create a line? No. Yes, it does create a line. Cool. Okay, I didn't. Let's separate this into a new section here where we're exploring now the idea of system, so that you can now match this up later with the fully narrated lesson. This is our little marker here that we're changing topics. And what we do have a matrix A, don't we? Okay, but that's not the one we want, is it? Oh, yes, it is. It's the same matrix. Okay. So this is our matrix A, and we're going to now ask ourselves for a vector C, NumPy dot array, and the vector C is 1, 5. For this vector C, what is the vector x that lands there after the transformation? That is going to be A inverse. I believe we computed A inverse already. Dot C and let's print x, and out comes a vector. So the vector minus 2, 3 is the solution of this linear system that we were showing here as two algebraic equations. It is the vector that answers the question that is asked by the system. But we understand it now geometrically. Now, if you look at it row by row in this form, if you look at the system of equations in this row perspective, you can imagine that I can rewrite these two equations. I can, well, rearrange it as y equals something. I can move the x to the other side in both cases, and I can have 1 minus x for the first, y equals 1 minus x for the first equation. I could have y equals 5 plus x for the second equation, and each equation represents a line. So if I were to imagine that each equation represents a line, I could plot the line represented by these two equations. Y equals y minus x, and y equals 5 plus x. All right, these are two lines. So I could plot these. Let's create an array of x values as numpy.linspace between, say, I played around with two values, obviously, here, and chosen two that gives me the range that I want to see. And so let's just follow along. And we can create a line as the general equation of a line is y equals mx plus b, where m is the slope, b is the y-intercept from our basic geometry. So let's create them both at the same time. So m1 comma b1, that's the first line, the first row, and m2 comma b2 is the second one. So we have those values from here. What is m1? It's the slope is -1, the thing that multiplies x. The y-intercept is 1. The slope of the second equation is 1, and the y-intercept of the second equation is 5. So we're defining here the y-intercept and slope of these two lines, and we're going to plot them. So let's do a pie plot dot figure. Let's do fig size equals, let's do a square figure 2 by 2. Let's do pie plot dot plot of the first line. So we're going to create x values, and in the y direction we're going to do m1 times x values plus b1. That's the first line there, mx plus b. And the second line, pie plot dot plot, x values is the same, but it's m2 times x values plus b2. Those are our two lines. And let's see, here's our result. We see the two lines are plotted here, and they intersect at a certain point. That point of intersection is the solution of the linear system of equations, the point that belongs to both lines, and we could actually, or we already know it. Did we create the inverse x? Yeah, here's the inverse x. That's the value, that's the solution. So we have the first, we could do a scatter here, pie plot dot scatter with the two components of x, and that is x0 comma x1. Those are the two components. We already know the solution. So let's plot that, and we get a nice ball there drawn in the point of intersection that shows that indeed the components of x are the point, correspond to the point that belongs to both lines, the solution of our linear system. So you see that the coordinates of the solution are right at the intersection of those two lines, and the correspond to the solution of the linear system, the point -2, 3, that belongs to both lines and satisfies both equations. So from this perspective, we're looking at a linear system row by row. Up to now, we've been looking at the matrices from the column perspective, which is very useful. It may be a more familiar perspective to you. You may have seen linear system of equations in your undergraduate class in this form. And so it may be this is natural. But the way that we were talking about previously from the column perspective is a way that you can generalize to multi-dimensions. If you're used to looking at the matrix problem to solve a linear system in this form, it already is hard to imagine it in 3D, but if you go to higher dimensions, then your intuition is pretty much gone. Whereas the previous point of view is one that we can indeed generalize. Okay. So now let's look at another possibility. We could also have done, NumPy has a built-in facility to solve the linear system of equations. So we could also have done x equals NumPy dot linalg dot solve with the matrix A and the right-hand side C, and then we would have obtained the same solution. So this is also available to us from NumPy. The dot solve. Now, suppose that we want to solve a linear system with a different coefficient matrix. We have a different example here with this coefficient matrix. Here it is. the rows. So the first column, remember, is where the I vector lands. The second column is where the J vector lands. We understand it as a linear transformation. Now let's look at it from the point of view of a linear system. So D equals to NumPy dot array of, what do we have? The rows -2, comma, -1, comma, 1, comma, 0.5. That is the matrix D. It's printed to see that we got it right. And let's compare. That is indeed the matrix that we wanted for this example. Let's plot the linear transformation with this matrix D. And it's not really what we wanted to see. We've encountered something similar in the previous lesson when we plotted 30 vectors that were a random linear combination of, in the previous lesson, A and D. These two vectors were collinear, so they landed on the same line. Any infinite linear combinations of them still landed on the same line. We were not able to traverse the whole space with them. And these are the vectors, in fact, that now we have put together as two column vectors of the matrix D. This matrix capital D is formed by the matrix from the previous lesson, small a and small d. They're collinear. So as a linear transformation, it has the effect of just squashing everything into a line. Now, if we were to try to do the inverse with numpy.lin_alg and this matrix, we're going to get an error. NumPy is going to complain, it's going to say, error, this is a singular matrix. I cannot give you the inverse. Now you can see here from the point of view of linear transformations why this might be the case. If the matrix D grabs every vector and squashes them all into a 9, what transformation could I possibly invent that unpacks that line into the whole 2D space again? It seems like an impossible thing to do. And that is why D is singular. It is not able, it doesn't have an inverse because there's no linear transformation that can take a line and explode it into the 2D space. Now, if we look at it now from the point of view of the row-by-row linear system of equations, as before, we can expand that out and write the two equations. Here's the matrix again. We have the rows -2, 1, 1, 0, 5. So here it is again, -2, 1. The 2 multiplies the x. And here's the other equation, moving everything to the right-hand side to unpack y. So now we can write, with these two equations, a linear system. So we have the same as before, x values equals, so let me write the equation. Let me actually write the two lines here in these notes for a future reference. Row by row, okay, we have these equations. And I'm going to write, the first one is y equals -1 minus 2x, and the second equation is y equals 5 minus x divided by 0.5. These are our two equations. And now we can write again two lines to represent these equations, as we did before. So x values equals some numpy.linspace. I did this before, and I played around enough that I found a nice range for these numbers, and it's -410. Since I did this ahead of time, I have that advantage. M1, comma B1 defines the first line. M2, comma B2 defines the second line. And that's going to be, let's see, the first line, what is the M? That's -2. The y-intercept is -1. For the second equation, we have 1 over 0.5, which is the same as multiplying by 2. So that's -2 multiplies x. 5 divided by 0.5 is multiplying by 2 again, and so that gives me a 10. All right, those are the, that's the those are the two lines. So let's do a pyplot dot figure. Let's do fig size again, square figure. Let's do pyplot dot plot with the first line. So we're going to do x values for the first array. For the second array, we're going to do the first line. So m1 times x values plus b1. That's our first line. Pyplot dot plot x values dot m2 times x values plus b2. And that should be it. And that is what we obtain. We obtain two lines. The lines are parallel, so they never intersect. The system has no solution. The matrix that formed the system is singular. Its columns are linearly dependent. As a transformation, it squashes everything into a line. There is no inverse that will take the transformed space back to where it was. This is called an inconsistent linear system. Now, if the right-hand side vector were itself collinear with the two columns of the matrix, then these two lines would be on top of each other and there would be infinite solutions. So let's try that. Let's create a vector. For example, the vector, or in fact, I don't think I need to compute it. I will just show it to you here. With the vector, remember the two columns of D, where are the columns of D? -2, 1, -1.5. So you can see here that the factor, that creates that line is a factor of 2 with a minus sign. So we've created a new vector that has that factor of 2 with a minus sign. It's -4, 2. If I create that as the right-hand side of the linear system of equations, then the right-hand side is also collinear with these two columns. And you can see that the first equation is actually the same as the second equation multiplied by -2. So the second equation adds no new information. The single equation viewed as a transformation takes a 2D vector as input and gives a scalar as an output. So what is the matrix? Think about the left-hand side. The left-hand side, 1x plus 0.5y as a linear combination of two. Remember, the left-hand side is a matrix times a vector. What is a matrix vector multiplication? A linear combination of the columns scaled by the vector components. What do we have now? We have, if we look at the equation as a linear combination of columns, then each column has only one value. So the columns, viewed as two columns, we have a single value in column 1, the number 1, and a single value in column 2, 0.5. So for this first time we encounter non-square matrices here, we can write this as a matrix vector multiplication of two column vectors that only have one number each, multiplied by the vector gives you a scalar. Now we're going to discuss this more towards the end of this tutorial, the idea of non-square matrices, if we get to it, I hope. But the key idea is that they represent transformations between dimensions. In this case, this non-square matrix takes a vector and outputs a scalar. It goes from 2 dimensions to 1 dimension. It is a linear transformation between spaces of different dimension. That is the end of the viewing the matrices as linear systems. That probably the whole idea of linear systems of equations is something that probably spent quite a bit of time in your linear algebra classes as an undergraduate, but that's all we have to say about it. Let's now look at the idea of a change of basis. All right, remember that we've discussed in various times that the matrix multiplied by the unit vector will give you the columns of that matrix. And we have used the word coordinates, but we haven't really defined them formally. So let's just to be rigorous here, the vector's coordinates are the scalars in the linear combination of the basis vectors that express that vector. So the coordinates here, x and y, multiplied by the basis vectors I and j, those are the coordinates that we're talking about. So now suppose that we were to express a vector, this is a vector minus 3, 0, as a linear combination of a and b. Not I and j, but a and b. These are the vectors. These vectors placed in the columns of a matrix like we've used before, the matrix C, we've already done that. Do I still have that matrix here? That's the matrix. These vectors, A and B, are the two columns. Now, we call I and J the standard basis, and A and B would just be different bases. Now, in the standard basis, this vector V has coordinates minus 3, 0. Now, if we want to ask what would be the coordinates of this vector if we were to use A and B as the basis instead, we're asking what would be the vector x such that c times x gives you v. This vector v right here. We know v has coordinates minus 3, 0 in the standard basis, I and j. What would have to be the coordinates if we were to express v with a and b as the basis? That is the same as asking to solve this linear system of equations, c times x, this new vector we don't know, gives you v. Those are going to be the coordinates if we were to express v as a linear combination of the columns of C. All right, so let's try to do that. We're going to create this new vector v. Okay, I'm going to add here a separation. This is going to be change of basis, just to leave some breadcrumbs so that you can compare your tutorial notes with the written out narrated notes. And we're going to create a vector v. The vector v is numpy.array. And what is it? It has minus 3, comma, 0 as coordinates in the standard basis. We know that we want to express it as a linear combination of I and j. We have to multiply I by minus 3. We have to multiply j by 0. Those are its coordinates in the standard basis. Let's now find the vector x that solves the linear system with matrix C and right-hand side V. That vector, that solution vector, minus 2, 1, that vector minus 2, 1 are going to be the coordinates of V in the new basis A and B. So so in other words, a linear combinations of A and B with scalars minus 2, 1 gives you V, the same vector V. Let's visualize the change of basis. The change of basis, the idea of going from basis ij to basis AB. Do we have A and B here defined? A. Oh, but we need different ones. We used this A variable differently before in this notebook. So NumPy dot array, we need the first column of this matrix C, 2, 1, and the second one, NumPy.array, the second column, 1, 2. A and B. Those are A and B. And now we have also an additional helper function that is called plot change of basis. That is built into our little helper with A, B, V. And that plot gives you here a plot on the left with the standard basis ij. The vector in red is V, had coordinates minus 3, 0. There it is, V. On the right-hand side, you see a transformed space where the basis vectors are A and B. On this new basis, A and B, V, which is the same as before, V didn't change. See, V is the same vector. In both worlds, it's the same vector, but in the transformed world, the coordinates of B, if we look at the picture, how many A's do we have? -2. How many B's do we have? +1. -2, 1 are the coordinates of V in this new world. And we got that by solving that linear system. So the matrix C represents, with its right-hand side, a linear system of equations, and it also represents a change of basis. On the left, the vector is represented by the coordinates on the standard basis, -3, 0. On the right, the vector is represented by the coordinates -2, 1 on the new basis. So this is a key idea, that the matrix C formed with the new basis vector as columns is the matrix that converts the coordinates from one space to another. We've highlighted that here in the notes as a key idea. The matrix C, formed with a new basis as columns, is the matrix that converts from the coordinate system using that basis to the standard basis. Now, here is something that one needs to think about carefully, right? C multiplies the coordinates, gives you the coordinates of the, converts the coordinates of the vector from the coordinate system using A and B. To the standard basis. So going the other way around, from the standard basis to A and B, we have to multiply by C inverse. That is why we need to solve Cx equals V to get the coordinates on the new basis. So if we wanted to apply a known transformation, suppose here, R, that's a rotation. Remember we did rotations only a little while ago? Suppose we wanted to apply a rotation to some vector that is expressed in the new basis, A and B. We know the rotation on the standard basis. We can work it out very easily. We already did. We know the vector I rotates this way, the vector J rotates that way. We can write it out. We know rotation matrix. But we have V in a new basis. What do? Well, we take V, we transform it to the standard basis, rotate there, and then transform it back to the new basis. And now we know what happened. So how do we do that? We need to multiply by C inverse to get to the standard basis, do the rotation there, and then multiply by C to get back to the transformed space. This is a composition of 3 transformations, which means we're going to have to multiply 3 matrices. We're going to need to multiply we're going to need to first change the representation of the vector to the standard basis, apply the transformation, and then change back. This is why we express these types, we have this type of equations often where we are using a change of basis and we're applying a known transformation in the standard basis, and the result of that is a combination of 3 matrices as shown here in this expression. Now, we do want to point out that not all matrices are change of basis. We already saw an example before where we had A and D. A and D are collinear. They cannot actually span the whole space, so they're not a basis. And so this section where we titled it a matrix is a change of basis really only applies for matrices where both columns are linearly independent, because otherwise we don't have a basis. We can't really do a change of basis with it. All right. So this is something to ponder about. We left it here for you to revisit and ponder about it. As the linear transformation, a matrix transforms one vector into a new vector under the same basis. We can stay in IJ all the time. We're just taking one vector and transforming into a different vector in the same standard basis. As a change of basis, the matrix can express the same vector's coordinates in a new coordinate system. So let me go back to this picture. We have V, before and after, is the same vector. Okay? As viewed as a change of basis, what we are doing is now representing the same vector, but with coordinates in a different coordinate system, the new basis. 2 ways of looking at a matrix. Now, to finish this part of the lesson, this second lesson, we want to look at matrices in three-dimensional space. We've been working in 2D space because it's easier to visualize things, but the intuitions that we develop, then we can generalize. Let's look at a few linear transformations in 3 dimensions. We've left also in the narrated lesson some links to some good videos that you can watch to help you out, to help you visualize, because in 3D it's already more difficult to visualize. In higher dimensions, it really is quite hard. Okay, so let's create a matrix. We do have a nice helper function to do 3D transformations, and let's create a matrix M. And this matrix, it's here rendered for you, and we have to enter it in Python as a list of rows. We're going to need 3 now, so let me just make my life easy to not make mistakes with the parentheses. I'm going to do that trick. So now I can fill it up, and I know that I don't mess up with my parentheses. And each one of this has 3 components. And these 3 components correspond, each element now we're going row-wise. And let's look at it again. 1, 0, 1, that's the first row. The second row is 1, 1, 0. The third row, minus 1, 1, 1. There's M. Let's print M to make sure that it comes out the way we want it. And it looks like it's correct. 1, 0, 1, 1, 1, 0, minus 1, 1, 1. Okay, there's M. So now we can plot the 3D linear transformation with this helper function, plot 3D linear transformation with M as an argument. And out comes a nice interactive figure, and this time we're going to use the interactive figure. You see that on the left-hand side we had this grid in 3D space. On the right-hand side we still have a grid, but things have been, sheared about a little bit. But we can move this and see that it is still a cube of grid lines. So it is a little harder to figure out what's going on already in 3D. It's a little hard to visualize. But the idea of a transformation as a matrix vector multiplication is the same as before. We can express the matrix vector multiplication as a linear combination of the columns of the matrix M scaled by the components of the vector. So if we were to consider applying M, this matrix right here, to a general-looking vector x, y, z, here it is the columns of M multiplied by the components of the vector, and that is the result of the matrix vector multiplication. The meaning of these columns also is where the unit vectors in 3D, in this case, land. So the first column is where the 3D unit vector I lands. The second column is where the 3D unit vector J lands, and we have a new unit vector usually called K, and that's the third column of M is where it lands. So now we do want to make sure that you're able to do this, and I do want to challenge you and to take out a little piece of paper, and you have the 3 columns of M, so try to make a 3D plot on a piece of paper and see how each unit vector is transformed by N. Let me give you just a couple of minutes to make a little drawing. Make 3 axes, x, y, z, unit vector I, just look at the unit vector I, and then try to see where it lands under M. Do another little plot, see the vector J. No, I think we put ij on the plane, and then we do k in the vertical direction. And try to do that. Just let's take a minute to do that. Next, we're going to discuss 3D linear systems for a little bit, and then we're going to take another break. So, well-earned break. We will make it longer now. We're going to make a 10-minute break, I didn't really look at the schedule if there's like some actual official break and snacks or something. No, okay. Okay. So we're just gonna do our own. This is just the lunch break. Okay. Okay. Remember these lessons are all written out for you, so you can revisit the material and follow along and fill any gaps. Make sure that you these little challenges that we leave here, you take the time to do that because they were helpful to us, and we think they'll be helpful to you. So now let's discuss 3D linear systems of equations. And it's similar to the two-dimensional case. We get a linear system of equations by now looking at the row perspective. And again, we ask, suppose that we have a vector u in the transformed space, and we want to find out what vector it came from before the transformation. And just like in the 2D case that is answered solving the linear system of equations. With the multiplication mx, we can write it out element-wise like we did before, or row-wise, and then take the right-hand side vector as some choice. In this case, we've chosen the right-hand side vector to be -1, 0, 2, and we have a linear system of equations. We can solve this using NumPy. Let's we already defined the matrix M, and we're going to define now the matrix of the right-hand side, that is NumPy dot array, and we need 3 components. These components were -1, 0, 2. -1, 0, 2 is the vector that we're giving you here for the example. That is the right-hand side vector, and we find the vector that lands there after the transformation by solving numpy.linalg.solve with matrix M and right-hand side U. Now we can print X, and out comes the solution. The solution means that the matrix takes a vector with coordinates -1, 1, 0 to a vector in the transformed space with coordinates -1, 0, 2. We can write this in general, of course, as mx equals u, and sometimes we call x the input vector and u the output vector. That's terminology that is also used. But now let's look at something interesting. Let's play with this different matrix. We're going to now play with the matrix here, 1, 2, 7, 0, 1, 3, -3, 1, 0, listed by rows. Let's do that. So let's define n equals numpy.array. I'm going to do the trick of putting my, do I have, oops. Yeah, that seems okay. Oh, is this this is a markdown cell. And 1, 2, 7, 0, 1, 3, -3, 1, 0. Those are the rows of the matrix, and let's make sure that is what we wanted. Let's compare 1, 2, 7, 0, 1, 3, -1, -3, 1, 0. There it is. That's the correct matrix. And let's now plot 3D linear transformation with n. Execute that. Now we see, it's, as I said, it's harder to visualize things in 3D already, but if I try to move around this figure, the transform space, I see at some point something a little bit iffy going on which is that in the transform space, it seems like the whole three-dimensional world got flattened out into a plane. And, it's hard to see from certain angles, but if I move this around, and that's why we wanted to use interactive figures here, you can see that this is actually just a flat plane. The matrix N transforms the 3D space onto a flat 2D plane living in 3D, but still flat. What is going on here? Well, if you look at the linear system of equations, and let me go back here. If you were to look at the linear system of equations with the zero vector on the right-hand side, and you were to write it out by rows, you would be able to manipulate here these three equations to realize that the last equation gives you y equals 3x. And when you plug that back into the first and second equations, you get essentially the two equations which are the same. One is a multiple of the other. You can pick any value of z, and then that will give you x and y to satisfy the system. We can call z as a free variable, and in fact, this system is a bit special, and using the zero vector on the right-hand side helps us figure this out. When we use the zero vector on the right-hand side, this is called a homogeneous system. So we're introducing here some formal terminology. And the set of all solutions of the homogeneous system, nx equals 0, is called the null space of n, sometimes called the kernel. And the null space of our matrix n is all the scalings of the scalar z, the third component of a vector, by these numbers. It is a line, a one-dimensional space. When you have the situation that the null space of a matrix has non-zero dimension, that is, the zero vector is not the only solution, then it means that the columns of the vector, the original matrix, are linearly dependent. So recall that we said that not all matrices can be a change of basis. We were in the 2D case before. Now we're in 3D, and it also happens that to be a change of basis, all the columns have to be linearly independent. In this case, the columns of n are not a basis for 3D space. The space spanned by the columns of n is two-dimensional. It's a plane. All the linear combinations of the columns of n land on a flat world. So the definition that is important here is the word rank. We call the dimension of the column space of a matrix its rank. This matrix N is a 3D matrix, 3 by 3. It multiplies three-dimensional vectors, but the output of this matrix vector multiplication has dimension 2. The effect of this matrix is to reduce the dimensionality of the vector space that it transforms. We can check rank of a matrix in NumPy with a built-in function, which is numpy.linalg.matrix _rank. And you can check now that the rank of n is 2. Even though it's a 3D matrix, its rank is 2, and so the output vectors all live in a plane. We call this a rank deficient or singular matrix. Let's now play with another matrix. Let's do L equals numpy.array. And the matrix, let me show it to you here. Here it is. 1 to 1 is the first row. One to 1. The second row is -1, -2, -1. -1, -2, -1. The third row is 3, 6, 3. There it is. And let's plot the linear transformation. Plot 3D linear transformation with L. And here's the result. You see in this plot that on the right-hand side, that's not good. Everything got squashed into a line. So you can drag this wireframe on the right-hand side however you like, but you can never see in 3D in that space. Everything lives in a line. And in fact, if you were to check with numpy.linalg.matrix rank for L, you get 1. The rank of L is 1, which means the dimension of the space spanned by the columns of L is 1. All the vectors that were transformed by L land on that same line, a one-dimensional space.
Is every rank-efficient matrix equivalent to some rectangular matrix as a transform? I mean, it should be, right?
I guess by a composition, by a decomposition, he says a rank-efficient matrix can be similar to a rectangular matrix because they changed by a decomposition. We're going to talk about matrix decompositions in the next 2 lessons. This is the end of this second lesson and a well-deserved break for everybody. Let me just show all the things that we've learned in this lesson: how to compute the norm of a vector, that a 2D matrix transforms a unit circle into an ellipse, the vectors that don't change direction after a linear transformation are the eigenvectors. Don't forget that wonderful thing. That's really cool. For any vector in the transformed space, you can find the vector it came from by solving a linear system. If we look at the linear system row by row and interpret each row as a line, the solution is the point of intersection. We know how to use NumPy linalg solve now. And in 2D, when the 2 rows are parallel, the system is inconsistent. There's no solution. I and J are the standard bases, and we can form a basis, form a matrix with any 2 pairs of bases, and then it transforms vectors from the coordinate system using that basis to the standard basis. So C inverse transforms the vectors from the standard basis to the new basis. We can apply a known transformation by transforming from one base to another, which means composing 3 transformations. We know that a homogeneous linear system is the one that has a 0 right-hand side. The solutions to a homogeneous system is the null space, and if the null space has dimension, any dimension non-zero, then we know that n is rank deficient. The rank of the matrix is the dimension of its column space. So we've covered quite a bit of ground in 1 hour. All of these are usually covered over weeks in a standard course, but we've looked at it from an intuitive point of view using our graphical helpers, and this is already all the foundation that we need to know to move into eigenvectors for the win. Next lesson, let's take a 10-minute break. So let's pull up the 3rd lesson of our little collection, eigenvectors for the win. All right. We saw before this very interesting behavior of a couple of vectors in the case that we looked at for a 2D, two-dimensional case that started by looking at all the unit vectors around a circle, and we saw that all the unit vectors around the circle were transformed into unit vectors around an ellipse, and the semi-major and semi-minor axis of that ellipse corresponding to these special vectors that don't get thrown off their span, and the effect of the matrix on them is just to scale them. This is, in fact, very, very useful, and we're going to dedicate this 3rd lesson to discussing eigenvectors and eigenvalues. As always, we're going to start loading our libraries, and now in this case, we're going to use again the inline back end. So I'm going to copy and paste to save a little bit of typing. I'm going to create a new notebook, Python 3. And this is going to be our lesson on eigenvectors for the win. Yes. All right. I'm going to load all of this in just one cell, and I'm going to cheat a little bit by copying and pasting from the written out lesson to save a bit of time. Okay? And let's first discuss the geometry of the geometric point of view of eigendecomposition. And we saw in the previous lesson that this unit circle by a 2D linear transformation got transformed into an ellipse. Now, a word of warning, in that previous example, we used symmetric matrices, and we didn't say anything, we just presented that, but now we have to be more rigorous and point out that only symmetric matrices will behave the way that we saw. Let's revisit that. We had the matrix A. This was our symmetric matrix. I haven't explained what symmetric is, but it means that the rows and the columns are interchangeable, and it's the same matrix. So they behave in a special way. So let's recap that again. We had 2, 1, and 1, 2 as our matrix. And let's print A and then also get the linear transformation of A and look at it. Here it is, 2, 1, 1, 2. I need to restart the kernel, right? Why am I getting the small images again? I'm inline. Re-execute. What's going on? Well, the default is false, so it should not be. Okay, well, mystery, but solved. Okay, there it is, the transformation that we were working with before. And we see that the 2 unit vectors got transformed to the columns of the matrix, which is what we've learned. So let's now repeat the process of looking at the unit vectors around a circle and the transformed version. We did that by creating a NumPy array from 0 to 2 numpy.py. And we had 41 of these to start with. We create a list of vectors as using the built-in zip function. And what do we use inside that zip? We have numpy.cosine of alpha and numpy.sine of alpha. So that is going to be the list of coordinate pairs for the unit vectors around the circle. We also want new vectors that are the transformed versions, and I'm going to do this the long way by appending the transformed vectors for I in range len of vectors. We're going to append new vectors from multiplying A with numpy.array of vectors element I. Now we can plot vectors, and this is what we did before, and we have the set of vectors around the unit circle. And if we use plot vector on the list of new vectors, we get the vectors around an ellipse. So far, so good. We've done this before. We also computed the semi-major and semi-minor axis. We found that semi-major axis was 3, semi-minor axis was 1. We've done that. I don't think we need to do it again. I believe that we can skip it. But now let's see. If you look at this, it's rather inducive of some imagination here. We learned in the first lesson that there's some special transformations: rotation, shear, and scaling. If we look at the effect of the linear transformation on the very vectors around the unit circle, we might imagine that we can go from the unit circle to this ellipse by a combination of a rotation and a scaling. It looks like we could do that. That's just, well, we get that idea, don't we? We get the idea that we might be able to stretch the horizontal vectors first from, the I vector, we want to take it from length 1 to length 3, and we stretch it. In the y direction, the stretching will be just 1. We don't want to change the length in the vertical direction. And then we can just rotate everything in 45 degrees, and we would get that same picture. That's what we think. So let's try it. Why not? We could try it. Well, let's first create the scaling transformation. S equals NumPy dot array. And remember the scaling transformation. Where do we want the I vector to land? Well, we just want to stretch it, so we want it to go to 3, 0. And the I vector, we want it to stay the same, so we want it to go to 0, 1. We have to remember that we're thinking in columns, but Python wants us to talk to it in rows, but it turns out this is a diagonal matrix that's got zeros, and so we are okay with that. And we're okay passing 3, 0, 0, comma 1. And I'm missing a parenthesis, square brackets here. And let's make sure that this works by doing print s. And there it is. That's a scaling matrix that scales in the horizontal direction by 3, and nothing, just keeps the same length in y. So let's create a set of vectors on an ellipse. So we're going to start with just an empty list for I in range len vectors. And I'm going to apply, I'm just going to do it the long way by appending the S dot operation, the matrix vector operation, with all the vectors in the original set, NumPy dot array vectors I. So I'm going to go over all of them one by one, append them, and make a list of the transformed vectors. And let's do plot vectors ellipse. There we go. And yes, that's what we wanted. We stretched everything in the x direction by 3 and didn't do anything in the y direction. Now, let's try to do a rotation transformation that rotates this whole ellipse by plus 45 degrees. Now, in the previous lesson, we wrote the matrix for a rotation by 90 degrees in 90 degrees in the positive, and you had to work out the rotation by 90 degrees in the negative angle. Now, we didn't do, how do you rotate by any angle? We didn't do that, but what I want to point out is that you never have to memorize a rotation matrix. You just have to think about where the unit vectors land and write where I lands as the first column, where J lands as the second column. If you look at this picture, and I'm seeing the I vector here is a little bit transparent, and by a rotation by 45 degrees, it moves to the unit vector at the 45-degree angle, I can know that the coordinates of this vector are going to be cosine of the angle, sine of the angle, both positive. If I look at the vertical unit vector j, it's going to land after the rotation by 45 degrees in the second quadrant here, where the x-coordinate has to be negative while the y-coordinate is still positive. So I can write where these vectors land, I from 1, 0 goes to cosine theta, sine theta. J from 0, 1 goes to minus sine theta. The angle is here, so that is the same angle as here. So that length down here in the x-axis is sine of theta. And in the y component is going to be cosine theta. So we have that J goes to minus sine theta cosine theta, and now we can put those columns together and write the rotation matrix. The rotation matrix appears in multiple applications in robotics and mechanics of all sorts, and normally undergraduate students in engineering have a great difficulty because they can never remember the rotation matrix. You don't have to memorize it. You can work it out each time by doing this little picture, and it will come out very easily. It'll take 30 seconds to work it out. So here is our rotation matrix. In our case, we're going to rotate by 45 degrees, which is pi fourth. So let's create that matrix. We're going to do theta is our angle, is NumPy dot pi divided by 4. And the rotation matrix is going to be NumPy dot array. And I'm going to make my life easy by organizing this as like that. And now I know the first row here is cosine. Remember, I have to talk to Python in rows. And so cosine NumPy dot cosine theta. And the second component is minus NumPy dot sine theta. Let's double check. Cosine minus sine. And then in the other row, we have NumPy dot sine theta, comma, NumPy, both positive, NumPy dot cosine theta. And that is our rotation matrix. Do I have extra ones? That one closes with that one there. All right, thank you. Oop. What happened? Okay. Now we can apply this rotation to the ellipse one. So I'm going to call it rotated. Again, I'm going the long way, but just being explicit here. We can do this in a shorter way, but not yet. In range len vectors. And we're going to create rotated by appending the transformed version of NumPy.array vectors I. Vectors, no, ellipse I. Ellipse. That is the vectors that we have, the list of vectors that we have up there. Now we're going to apply a rotation to it. And let's plot the vector list of rotated vectors and check it out. That looks pretty much what we wanted. It certainly looks like it. It looks like we've recovered the original figure. Let's have a look at the two linear transformations. We applied first a scaling, then a rotation. So let's look at those two linear transformations with the help of our little helper, the function that goes like this. Plot linear transformations. Remember, we've applied S first and then R. We applied the scaling, then the rotation. Let's look at that. All right, so yes, the scaling did what we wanted it to do. Here are the unit vectors. They got scaled. And here there's the rotation. That's interesting. Do you notice anything that seems as cue to you in this result? The scaling did stretch like we wanted. 3 in the x direction, 1 in the y direction. something looks off to me in the second plot. Any ideas? No? Any ideas? Let me give you a hint. Which were the vectors that landed on the semi-major and semi-minor axis? In our experiment before, which were the vectors that landed on the semi-major and semi-minor axis of the ellipse? They were two very special vectors that the eigenvectors. Were they? Yes, they were. They were the eigenvectors landed on the semi-major and semi-minor of the ellipse. And then we found that those two vectors actually did not get knocked off their span. They only got scaled by the whole transformation. Now, what we're seeing in this plot initially, what are these two vectors? These are the two unit vectors. The two unit vectors got scaled, stretched in the horizontal direction by 3. And now we see for the ellipse that the arrow that we're seeing coincided with the semi-major axis seems to be the transformed version of the basis vectors, but we know that's not the case. We know that the eigenvectors should be there, not the unit vectors. So our intuition, our visual intuition of trying to replace this transformation by a stretching first and then a rotation didn't quite work like we expected it to be. Our intuition seemed like the right idea at the time, but it's not giving us what we need. It's not the same as applying the transformation, what's called A. It's not the same. Applying the scaling and the rotation successively as a composition of transformations is not the same as just applying A. You agree with me? Because if it were, then the unit vectors wouldn't be there. That's the place for the eigenvectors to be at. So this is going to blow your mind. To actually get the same picture that we get from A, what we needed to do was rotate minus 45 degrees, then scale, and then rotate back 45 degrees. Our intuition wouldn't have revealed that because rotating a set of unit vectors looks the same. Still the set of unit vectors. Rotating a circle doesn't give us anything. So we know from the previous discussion that the vectors that should be landing there are the eigenvectors. So in fact, so I'm going to skip in the lesson, in the written out lesson, we expound on that idea by plotting the eigenvectors together and then the with before and after the transformation, and showing that the eigenvectors actually are not landing where they're supposed to land with this combination of a scaling and a rotation. To complete the transformation, what we need to do is first rotate 45 degrees to the right, which leaves the plot unchanged for the unit vectors, then scale, and then finally rotate 45 degrees to the left. So we're going to need to look at how to rotate negative 45 degrees. To rotate by a negative angle, if I go back to this picture, and I recommend that you do, in the interest of time today, we won't, but you should, after you revisit this, in a piece of paper, make the same drawing here, but with a negative angle. And convince yourself that if I rotate by a negative angle, arbitrary angle, theta, the rotation matrix that you're going to get looks like this. Cosine theta, sine theta, minus sine, cosine, and this matrix turns out to be the transpose of the original rotation matrix that we worked out previously. The transpose means that we are swapping the rows and columns. So you should check that using a piece of paper. Negative angle gives me transpose of R, where R rotates by a positive angle. And you can compute it, of course, with Python, so we could for any matrix here, what we're showing here is that you can compute for any matrix. This is a side note here, so I'm not going to do it. I'm creating a matrix B as 199 to 1000, just to make the difference between the numbers big enough that you can see the difference between print B and print transpose B. Here's B with 1, 2 in the column. Here's B transpose with 1, 2 in the as the first row. So this is a side note to show you how to compute the transpose with NumPy. So let's now look at this result of multiplying these three matrices. Little note here so that we know what's going on in these. And we're going to look at the combination of R multiplied matrix multiplication by the scaling matrix multiplication R transpose. Okay, and I need the parentheses. And now, and what was A? That is A. Okay, that is how we complete the decomposition of A into a scaling and a rotation. Two rotations, one by R transpose and one by R. And this is pretty neat. So let's plot it. Plot linear transformation of, now we're going to give it as argument here, R matrix multiplication S matrix multiplication R transpose. I like extra air around that. And this is indeed the same transformation as A. So that's very interesting. Now let's visualize the transformation R transpose. And we're going to add to our plot the unit vectors that were aligned with the eigenvectors. We can do that, the plotting function, linear transformation function by default shows you just the unit vectors, but we can add extra vectors by passing optional arguments. So we could do the following. V2 is going to be the eigenvector that is obtained. Did I compute U1 somewhere? I think I didn't do it. That's the part I skipped. Yeah. Where is U1? Where do I define U1? Because I have V. Maybe this way? Aha, here it is. Okay, so U1 is the unit vector. No, it's not the unit. It's the semi-major. U1 is the vector in the direction of the positive semi-major axis of the ellipse. U2 is the semi-minor in the second quadrant. So the first coordinate is negative, the second coordinate. We did that in the previous lesson. I tried to skip it to save some time, but that didn't work for me. So let's, I'm just going to copy and paste. This is not very good, but I'm noticing that we're running short of time, so I'm going to do that. And you would be able to do that as well if you pull up the lesson from the GitHub repository and obtain these two vectors. We did this already. That's why I wanted to skip it. We did it in the previous lesson, so there's no new information, but we need it again in this notebook. U1 and U2 are the transformed vectors that land on the semi-major and semi-minor axis of the ellipse. And what we need is V1 and V2, which are the, yeah, of course. Of course. I'm going to do something cheating, and I'm going to do semi-major equals 3 because I know it's 3, and semi-minor equals 1. And then re-execute this. And now to get to get the vector that landed there after the transformation for each one, V1 is going to be the vector that, so let me get A inverse. I don't know if I have A inverse. I'm going to compute A inverse as numpy.slin alg inverse of A, and V1 is the vector that landed on U1 after the transformation, so we need to multiply by U inverse, and V2 is the vector that landed on U2, so I need to multiply by the inverse again. All right, these are the eigenvectors, V1 and V2. They land on the semi-major and semi-minor axis, and now we're going to plot the linear transformation. This is going to be a bit hard to see. R dot transpose, this is the first linear transformation that we apply, the transpose, and on V1, V2. These are the eigenvectors before the transformation. As the default of this function is to show me the unit vectors. The unit vectors are shown here, the horizontal and the vertical one. But in addition to the two unit vectors, I see additional ones, this one and this one, which are aligned with a 45-degree angle here minus, 135 degree here, whatever it is. After the transformation, which is R transpose, the rotation by a negative angle 45 degrees, the ones that seem now in the diagonal are the transformed version of the unit vectors, and the ones that landed on the axis are originally the eigenvectors. They got transformed from being diagonal to landing on the axis. Okay? Now we're going to stretch. Remember, the stretching is going to stretch on the horizontal by 3 and stretch by just 1 on the vertical. And so it's going to be the eigenvectors that get stretched. I've rotated it in such a way that the eigenvectors landed on the axis. Now I stretch them, and then I rotate back. That's what we're going to do. So I'm going to need two intermediate vectors. I'm going to call them EI and E1 and E2. E1 is going to be just applying the R transpose, so the rotation by minus 45 degrees. 2, I'm going to apply that operation to V1. All right, so I'm applying the transpose of R by matrix multiplication, by matrix vector multiplication to V1 to transform it, and E2 is going to be R transpose. That's the matrix I'm going to apply by matrix vector multiplication to V2. And now I'm going to plot the linear transformation, the next one that I need to do, which is the scaling with the additional visualization of E1 and E2 to help me visualize what's going on. Now you see that the transformation S, which is a scaling by 3 on the x direction, by 1 on the y direction, has stretched these vectors that are E1 and E2, are eigenvectors. Now I can see the final case, the final step, which is plot. I'm not going to save them, I'm just going to feed them into the function, plot linear transformation. I'm going to feed R, the final rotation, and the two vectors that I want to plot is the scaling applied to E1 and the scaling applied to E2. So I am doing the transformation of E1 and E2 by the scaling right on this line here. And I can plot this, and I see now, before the transformation, they were lying, the eigenvectors already stretched, were lying on the horizontal and vertical axis. After the transformation, the eigenvectors now are indeed in the semi-major and semi-minor axis of the ellipse, which is where we expected them to be in the first place. So now we confirm visually, geometrically, that the combination of these three transformations is doing what A does by itself. A is equal to R times S times R transpose, which is the eigendecomposition of A. Here it is. This is the eigendecomposition of the matrix A. A is square, and it's symmetric, and all sorts of things, and so we will want to see how we can generalize that. All right. In our previous discussion, we also figured out that the matrix that undoes the effect of another matrix is its inverse. Now, in this case, we've worked out a rotation by negative 45 degrees, and we figured out that the rotation by plus 45 degrees is the transpose. So what's going on? Well, it turns out that this R is a special matrix, it's a special kind of matrix that has the property that its transpose is equal to its inverse. This is called an orthogonal matrix. R is called an orthogonal matrix because its transpose is equal to its inverse. The columns of this of an orthogonal matrix have to have unit length, and in our example, it means that the eigenvectors of A are orthogonal because we were using the eigenvectors in the columns. This always happens with symmetric matrices, and the discussion that we had until now is valid just for symmetric matrices, but we were not telling you because we wanted to just work it out. But if we want to do the general case where the matrix is not symmetric, then we have some more work to do. We've only been playing around with symmetric matrices, and this is a little bit tricky, and I encourage you to revisit this, but I'm not able to fully satisfy you with a careful explanation in the interest of time. That's why we've written it all out for you. But in the general case, we know that the effect of the matrix A on the eigenvectors is just to scale them. They land on their span. So we can write this type of relationship AV1 equals a scalar times V1 for the eigenvectors. And if we were to stack the equations for the two eigenvectors where we put the eigenvectors as columns, then we would be able to write the two equations together as a matrix equation as shown in this line here. You will need to take your time after this tutorial to revisit this and think about it. But now let's suppose that we use C as the symbol of the matrix that has the eigenvectors in the columns. So in the left-hand side here, we have the matrix A times C with the eigenvectors as columns. On the other side, you have C times D, where D is the diagonal with the eigenvalues. If we multiply by C inverse on both sides, on the right-hand side, you get CD, C inverse on the left-hand side of the equation, and just A on the left, because C times C inverse is the identity. So you can see here why we call A a diagonalizable matrix, which means that we can, again, multiply by C and C inverse to just isolate D, the diagonal matrix. We can always transform the action of A into a diagonal matrix and a change of basis, essentially. If you remember our discussion of change of basis before, it had this form. So we're saying that to a change of basis, A has the same effect as a diagonal matrix. That's why it's called diagonalizable. A and D, by the terminology of linear algebra, are called similar. Their effect is the same to a change of basis. And this is a key idea in linear algebra as well. Now, if we were to try to visualize this whole operation, this whole idea of what eigenvectors do for a general matrix that is not symmetric, here we have an example. A different matrix that is not symmetric. Let's call it A again. We're reusing the variable numpy.array, and it's 1, 0, the first row. Second row is 1, 3. Let's print it to see that we got the right thing. And indeed, 1, 0, 1, 3, it's correct. We also have a function that we haven't showed you that is a custom function that will illustrate the eigen decomposition. Is plot eigen on A. Try it. Plot eigen gives you now the set of successive transformations that are contained in the eigen decomposition of A. First, a change to a new basis, then a scaling, and then a change back to the standard basis. We get an ellipse as before. Note that, well, we're going to see that in the next, we're going to see in a little bit, I don't know exactly when, that the eigen vectors are no longer going to correspond to the semi-major and semi-minor axis of the ellipse. Now, the next thing that I want to do is to show you how to compute eigenvectors, eigenvalues, and all of this in Python. All right, and we have a built-in function in NumPy, numpy.linalg, called eig. In the lesson and the written out version, we give you actually the link out to the documentation, so you can follow the documentation and read it to see what its output is, because it's going to give you two things. It's going to give you, the first element of the output is actually the eigen values in a 1D array. The second output is a 2D array with each eigenvector as a column. So if we were to do linalg numpy.linalg.eig of A, but the first element of the output is an array, a 1D array with the eigenvalues. If we were to do numpy.linalg.eig A, and the second element of that output, it's giving you a 2D array with the eigenvectors as columns. We can display the eigenvector that corresponds to the eigenvalue using a cute zip function here that maybe I'm able to skip. Where is it? Because I want to show you SciPy. Here, we're just plotting the eigenvalues and eigenvectors, unpacking the result of linalg.eig into these two variables, and then using zip to show them side by side, the eigenvector that corresponds to 3, the eigenvector that corresponds to 1. This is explained in the lessons, written out for you, but I don't think we need to do it. What we could do is create the actual decomposition. To create the decomposition, we would need to turn that 1D array here, this 1D array that contains the eigenvalues, into a diagonal matrix. It's a 1D array with just the two eigenvalues together. We want to turn that into a diagonal matrix. So for that, we can use the .diag, NumPy .diag. So we could do, so we already have the eigenvectors here. Let's unpack eigenvalues, comma, eigenvectors equals NumPy dot linalg eig of A. All right, now eigenvalues, let's do C equals eigenvectors. So this is the matrix. This is the 2D array that contains the eigenvectors as columns. Then we could do the decomposition of A as C matrix vector times the diagonal matrix that contains the eigenvectors as diagonals, NumPy dot diag, and we feed that as argument the eigenvalues. And this multiplied by the matrix sin the inverse of C. Inverse of C. Those are the components of our decomposition, and let's print the result and see if it matches A. And indeed, it is the same as A. Like it should. Now, another way to compute eigenvalues and eigenvectors with Python is to use SciPy. SciPy is pretty lovely, in fact, and it can also make your outputs beautiful. And so let's import SciPy, and we need to give it some initialization to plot beautiful mathematics. In it, printing use LaTeX equals mathjax. That's to configure the printing to look beautiful. And so now we can use the built-in matrix data type. So let's create A now using SciPy. SciPy.matrix. The matrix built-in object. Now we can feed it as before, a list of lists with the rows 2, 1, 1, 2 was the symmetric matrix that we use. And now if we print A, we get this beautiful output from SciPy. We know that this one is symmetric, and we could check with a logical expression that A is equal to E transpose. Indeed, it is, because it is symmetric. We could now obtain the eigen decomposition in one line with A dot diagonalize. Well, let's print it. Let's print D. That's the diagonal matrix containing the eigenvalues in the diagonal. We can also get just the eigenvalues on their own. If I do A dot eigenvals, it gives me the eigenvalues on their own. It also indicates, after the colon, the multiplicity of the eigenvalues. Sometimes a matrix can have repeated eigenvalues, and that is indicated by the output of the SciPy method here. So let's, like for example, if I do SciPy dot, we can create a identity matrix with SciPy.I, I for the letter I suppose, and that's an identity, a 2 by 2, you give it the dimension here in parentheses, so that's an identity. And if I wanted now to know SciPy.I, the unit, the identity in 2 dimensions, and I wanted the eigenvalues of this matrix, I'm going to get now 1 colon 2 because the eigenvalue 1 appears twice. That's the second result here, the multiplicity of the eigenvalue. Now, let's create a shear matrix using SciPy. One comma 1, 0 comma 1, and show you that, well, let's print it. Here's shear. And show you that if I do the eigenvalues of this matrix, we again get the eigenvalue 1 with multiplicity 2. That's an indication in this case for the shear matrix that we are going to find problems if we try to invert it. We discussed before that if the null space of a matrix has less dimensions, so I think that probably this is more theoretical and we are running out of time, so I'm going to leave that for you to read and just discuss the application of the eigenvalues now. So we do have a little bit more filling up here a little bit of the formal content in the lesson for you to read afterwards. But let me just discuss some applications. I'm going to discuss the application to the PageRank algorithm straight ahead. We do have other applications in the lesson, but let's discuss the PageRank algorithm. We're supposed to end at 12, right? Yeah. Let's just discuss it with this example here, just so you know where it comes from. The PageRank algorithm, the original Google PageRank algorithm, now of course Google, web search works with many more advanced algorithms, but the original PageRank algorithm would count the number and quality of links to a web page to determine a rough estimate of its importance. And the way this would work is, suppose that you have in a network that has only 4 web pages, like shown in this figure. Web page A would have links to B, D, and C, and it passes its importance in equal measure, 1/3 to each. Page B has links to C and D, and it passes its importance in equal measure to these 2 pages that it links out to, 1/2 each. So you see in this relationship from this network diagram that A passes 1/3 of its rank to BCD, B has 2 links, it passes 1/2 of its ranks to C and D, C has 0 links, and D has 2 links. And so you can construct what's called an importance matrix, where each column here represents 1 web page, A, B, C, D. A is passing 1/3 of its rank to B, C, D, and that's shown in this column. B is passing 1/2 of its rank to C and D, and that's shown in the second column. C has no links, that's the third column, and the final column represents D. So with this matrix, one of the problems of this matrix, like we said, C has no links, so this columns of the zeros is a little bit of a problem. So you finally fill this matrix, this column of zeros, with 1/n, where n is the total number of pages. And then there's an extra step of damping this effect with just an equal random likelihood of any page being visited, and that's represented by the last term here. Now, the key idea is that this matrix applied successively leads to a steady state, and you can solve for that steady state via an eigenvalue problem. Due to the time that we have today and the voluminous materials that we prepared. We are unable to show you, but I'm happy to report that this is public and you can follow it. And in this example that we have here, you can solve an eigenvalue problem by iteration, and the result of this problem is an eigenvector that represents the ranking of each page in terms of importance. So the result is an eigenvector. The eigenvector here would be, each term corresponds to one of the web pages. And you see, for example, that this page is this second component has the smallest value. That would be the page with least importance. This component here, the third component corresponding to web page C, has the highest importance. And that would be, of course, the top hit in the search, the page with highest importance. So the take-home message here is that this whole algorithm is an eigenvalue problem. What we have provided here is the simplified version. You can follow it along and really compute it. We have a final exercise that I encourage you to do later with a network with eight web pages. And you can write this down as an 8x8 matrix, feed it into the algorithm, and solve the eigen problem. We have two other applications presented in this lesson. One is to, here just after SciPy, one is to ecology, where the eigenvector represents a steady state of an age distributed population where different ages have different mortalities and birth rates, and you can build a matrix for that. And the result is a steady state of the age-distributed population. Here's an example also applied for these types of applications. So they're called Markov chains. They have many applications in economics and in various other fields. And if you want to take the time to follow these examples that we provided here, I'm sure that that will also be illuminated. I'm sorry that we've not had time to show it to you, and I hope you do find it interesting to complete these lessons afterwards. And thank you so much for sitting here for 4 hours, and I hope that we've given you a good foundation to continue studying linear algebra afterwards on your own. Thank you.